University to promote the scientific know-how or the knowledge in astronomy and astrophysics. For their benefit, we are sure we can arrange seminar in the coming days. Because of COVID-19 pandemic situation, it is not possible to bring all the participants at the university campus. So this is the first time we are organizing this kind of seminar online. So I hope that this seminar will give you benefit to understand the subject. So finally, I want to say that the support from engineers of computer center of our university, the other supporting staff and research scholars in my group, it is possible to arrange this program. With this word, I want to pass on this microphone to our head of the department, Professor Suman Chatterjee, to say few words.
Good morning to you all, faculties, research scholars and students attending the webinar. ICARD and Physics Department NBU is organizing a one-day introductory seminar on astrophysics and cosmology. We in Physics Department has a long tradition of organizing seminar symposia in our North Bengal University campus. But due to the present pandemic situation, we are organizing it as a webinar. As you know from Professor Paul's address that there are more than 350 participants here. So it is arranged in YouTube as well as in this Google Meet. So I ensure that the seminar will be profitable and fruitful for everyone present here. Thank you for your participation in this seminar.
In a few minutes, we are starting our first lecture by Professor Devi Prasad Duwari. Professor Duwari is the director of MP Birla Planetarium in Kolkata. He is a very good speaker from the beginning. That means from the students to everybody who are not students, they enjoy the talk delivered by Professor Duwari. Professor Duwari did his PhD under the great astrophysicist and cosmologist, Professor Jayanta Vishnu Narlikar. He visited many countries in the world for giving talks and for academic purpose. He is a vibrant person from whom we get many things, and he also awarded with many awards from India and abroad. So I hope that his lecture will help you to understand many of the things not understood So I request Professor D.P. Duwari to start your lecture, please.
A very good morning to you all. It's really an honor and privilege for me to be invited for this seminar on Introductory Astrophysics and Cosmology being organized by the ICARD at Physics Department of North Bengal University. And I'm personally indebted and want to thank Professor Bikash Paul for remembering me and inviting me for giving this lecture. Going through the program list, I could realize that apart from me, all the other speakers are really luminaries in their field. And they will be giving amazing lectures, and all the students and participants will get tremendous amount of benefit on the different aspects of astrophysics and cosmology that they're going to speak. So I decided today that as an introduction, I should initiate the participants in this coming 1 hour that the organizers have kindly given me to talk about the whole subject of astrophysics and cosmology. But it will be a snapshot survey because thousands of scientists over decades are working on this field very actively. And it is almost impossible to encapsulate all the knowledge, all the information in a 1 hour session. So I will try to talk about the salient features which are actually fueling the present day cutting edge research in different aspects of astrophysics and cosmology. I will basically start by presenting a PowerPoint presentation with which I want to deliver my lecture. Is it visible? Is it visible? Okay. The title of my talk is Our Cosmic Consciousness. Now the phrase, the cosmic consciousness has been used in various terms. Somebody uses it in a theological way. Somebody uses it in a metaphysical way. But my approach today is to talk about the sky and the unknown objects in the sky, which has fascinated human mind from millennia. And especially in the last 2 centuries, the tremendous amount of advancement in their understanding and their observation has created a unique situation whereby most of us have realized that the answer to our deepest queries about nature probably lies in the cosmos. So, in these difficult days of pandemic, COVID-19 pandemic, when human mind is getting troubled by different aspects, by different premonitions of danger, I have found that a huge number of people are getting tuned up to very basic questions that are always there in our mind, and obviously to the skies. So let us begin. Thousands of years used to look into the sky. They used to wonder, what is sky? Where is sky? What are those objects, the lighted dots that we call stars? And is there any connection between the stars and the earth? With these set of questions and queries, the subject of astronomy was born. So astronomy can be considered as one of the oldest subjects that human minds have dwelt upon. At the same time, given the huge number of news items that you regularly get to see in the television channels and newspapers, you get an idea that it is also one of the most happening subjects in the recent time. Astronomy is a subject, as a power that it can tell us what was the physical situation in this particular region that we call Earth in our solar system millions of years back. At the same time, it can give us a hint what can be the situation in this part of the universe millions of years later. So spanning a vast expanse of space and time, the subject that deals is astronomy. And scientists all over the world are realizing that soon the 21st century may be termed as a century for astronomy and astrophysics. As a result, for the last 50 years or so, a tremendous amount of input in terms of resources, in terms of human mind, in terms of finance, is being given for research in astronomy and astrophysics for observational purpose. Just to give you an idea, in this inhospitable terrain in the Swiss Alps, they have built this observatory called Sphinx Observatory. Why? Because they want to see the sky in a very clear mode. But one of the best is Mauna Kea, one of the smallest island in the Hawaiian archipelago. 6 countries have created 9 observatories, and the smallest one cost is around $50 million. So you can understand what a huge amount of effort is being going to understand the cosmos. But especially for the Indian students and researchers, it is a very happy news that the largest telescope, that it has not yet been started. The name of the largest telescope is TMT, a telescope with a 30-meter diameter mirror at the heart of it. And 5 countries are actively collaborating to create this telescope: USA, Canada, China, Japan, and India. The Indian governments in 2014 have earmarked around 1,500 crore rupees for this telescope as Indian contribution. So you can understand what a big amount of effort is being done from India as well. But it is not only the optical light of the electromagnetic spectrum that reaches us from the heavenly objects. The radio wavelength also reaches us. And there is a tremendous activity in the radio astronomy in the last 30-40 years as well. This is the famous picture of the 100-meter diameter Effelsberg telescope in Germany. And there are a huge number of such radio telescopes, the biggest one in size in India as well, GMRT. But we all know that India is collaborating deeply with international other countries, other organizations. SCA, Square Kilometer Array, 130,000 small dipole antennas in Australia and 200 dish antennas in South Africa will be linked up to produce unimaginable power resolution to observe the space. And India is one of the main associates of this program. And you all know about LIGO, 2016. After almost 100 years of the general theory of relativity, whereby we came to know that 2 very compact objects moving in space can create a disturbance in space and time, which will propagate with the speed of light, and they will be called a gravitational radiation or gravitational wave. And those gravitational waves are detected 4 years back in 2 fantastic observatories in US, LIGO project, Laser Interferometric Gravitational Observatory. And we are all happy that India is one of the first international collaborators and associate of this LIGO project. India has started building its INDIGO project, the Indian Gravitational Observatory. And that's a very fantastic thing. So with this news of spot of activities in the astrophysical scenario, let us actually start the subject in earnest. Thousands of years back, when our ancestors used to look into the sky, they used to wonder what is the meaning behind those lighted dots, but they couldn't find an answer. But in their desperation, what they did, they chose different parts of the sky, identified closely spaced stars, joined those stars through straight lines, and created imaginary figures. In this way, the whole sky was divided into 88 regions, each region being governed by an imaginary figure which we today call constellations or Taramandal. You may be wondering that in today's digital world, what is the big use of knowing their imaginary names and imaginary features and their relative positions? But to me, even today, they are very relevant. Just to give you an idea, suppose a bunch of you has gone for a hitchhiking trip, night has happened, moon is not there in the sky, you have lost your way. Suppose somebody in the morning has told you, if you go in the southern direction, there is a locality, but which is the southern direction? If you happen to see the Shaptarshi Mandal, 7 stars like a question mark, take the last 2 stars, join them in your mind, produce it onto the sky, it will hit up on a single star, and that star is the pole star. The moment you get to know the pole star, you know which is north, south, east, and west. So even today, these sort of imaginary signs and signatures do play an important role in our understanding of nature. Let us talk about the sun, earth, and the moon. You may ask, what is big about it? We have all learned in our kindergarten days. But amazingly, if I ask the question, what is the average velocity of Earth around the sun? A lot of people will start scratching their heads. 29.5 kilometers per second. Can you imagine a car in 1 second moving 30 kilometers? But don't forget, you, me, 780 crore of human beings, millions of lives staying on the surface of the earth. Every second of our existence, we are moving at a speed of around 30 kilometers. Though we think that we are sitting or standing tight. Amazing. For example, we all know that Earth is going around the sun around an axis, and it goes around itself around another axis. And these two axes are not parallel. They're inclined at an angle of 23.5 degrees. And it is just for this reason season changes occur on Earth. For example, if you take the position of the Earth on your right-hand side of the moon, because of the 23.5 degree tilt, sunlight is falling directly onto the north and slanting onto the south. So it will be summer in the north because the amount of energy that will be absorbed and re-radiated per unit volume, per unit area will be more than in the south. And 6 months later, it is just the opposite. It is now summer in the south and winter in the north. You may again ask, what is the big deal? But my friend, you know, if there were no change of seasons, what would have happened? If there were no change of seasons, there would have been no ocean currents in our oceans. If there are no ocean currents in our oceans, there would have been no air currents in our atmosphere. And if there are no air currents in our atmosphere, clouds would not have born somewhere and gathered somewhere else and give us rain and fresh water. Life would not have been possible because just after it was born, Earth would have been a barren desert. So you and me exist now. It is because of this accidental tilt of 23.5 degrees. It is amazing. For example, solar eclipse. It's a wonderful, fantastic natural phenomena and a wonderful sight, right? And you all know why does it happen. Sun one side, moon in the middle, Earth at one side, sun's rays falling onto the moon's surface, moon's shadow falling onto a patch of space on Earth, and people staying on that patch of space will see as if the sun is covered by the moon. But it was during the solar eclipse, a total solar eclipse, not only the Earth experiences a beautiful scene, but just for example, this one taken from satellite, how the shadow of the moon is passing over the globe of the Earth, the path of the total solar eclipse. At the highest point, it can be around 950 kilometers in its width. But it was during an eclipse, sun was discovered as a new avatar. Scientists found out from the surface of the sun, milky white radiation coming out, which cannot be seen on other times. When they asked themselves the question, what is causing this, they were amazed with the answer. They found out from the surface of the sun every second, on an average, 16 lakh tons, 1.6 million tons of charged particles are coming out. These charged particles, as they move through the magnetic field of the sun, they produce this milky white radiation. The average velocity of these charged particles are 460 kilometers per second. With that speed, they have enough energy, they have enough momentum. If they hit any atom or molecule, it will instantaneously break apart. So basically it means after the lecture, when I go and stand on the sun, the charged particle coming from the surface of the sun, the moment they hit my body, within fraction of a second, my whole body should disintegrate. But I'm alive. How? I will come to that. Tides, a very important and interesting phenomena. It is just because of the tides, millions of years back, the first forms of life could come onto the land. And from there, through evolution, we have arrived. So that the human life, that other lives are there, it is because of the tides. And you all know why tides are important. But why does tide occur? It is not just the moon which is gravitationally attracting the water on the earth. It is the interplay of the moon and the centrifugal force and other forces. As a result, the tide cannot be defined as a force, but rather a force derivative. And that is the reason instead of 2 in gm1 m2 by r square, it becomes m1 m2 by r cube effectively. And that is the reason, since moon is 384,000 kilometers away and sun is 15 crore kilometers away, moon wins. But a lot of our teachers never tell us, sun also attracts the water body on earth. Do you know how much? 47% than the moon does, not a small amount. Though sun is gravitationally attracting earth, 173 times more than the moon, but it was because of the force derivative nature of the tide, we actually get to see a tide. So that is the important aspect of a tide and how is it important to our earth. Now let us talk about the moon. Beautiful picture taken from the surface of the moon. What is moon? According to 99% of the scientists, 452 crore years back, a huge cloud ball of gas and dust, rock, came and slammed onto the earth. With such a force, huge amount of material got gouged up and was thrown up into the sky. They couldn't go away forever, but going to a very vast distance for millions of years, they condensed, coagulated, coalesced, and has given birth to our moon. So the moon was born from the Earth itself. This theory has been subscribed because if you take the different aspects of the geological aspect of the moon and the Earth, the surface, features, and the chemistry, 98% of the scientists believe on this collision ejection theory. Though there are three other theories, co-creation theory, capture theory, and fission theory, but this is the most subscribed. You all know light travels at a speed of 3 lakh kilometers per second. So sun and earth distance can also be termed as 8.2 light minutes distant. That means light takes 8.2 minutes to come from sun to earth. But it physically also means whenever I look into the sky, deeper I am looking into my own past. So that is the reason a travel in space is not just a travel in space, but a travel in time as well. And the first stop of our journey is obviously the solar system. These are the colorful pictures of the main avatars of the solar system. Sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. The poor Pluto has been kicked out. Sun, our nearest star, our guiding star, the only source of energy that is provided for life to happen on Earth. What is sun? Sun is a ball of gas, you have all learned. But tell me, if I take a football, pump in a lot of colored gas, cut up in the football, will the gas remain like a ball? It will diffuse out. Then how come sun being a ball of gas is not diffusing out into the sky? What does the scientist say? According to the scientist, 460 crore years back, there was a huge cloud of gas and dust floating in space. In terms of number of particles, it was made up of 91% hydrogen, 8% helium, 1% rest other elements. In terms of mass, 75% hydrogen, 24% helium, and 1% rest other elements. The average temperature of this gas cloud was minus 240 degrees centigrade. At this very cold temperature, out of the four fundamental forces of nature, only one type of force comes into play, and that is the force of self-gravity. The force of self-gravity will attract the periphery of this gas cloud toward the center. As the gas goes toward the central density rises. As the density builds up, the pressure builds up. As the pressure builds up, temperature rises. And starting from minus 240 degrees centigrade, the temperature rose to a fascinating level of 1.5 crore degrees centigrade, which is enough to initiate a thermonuclear fusion reaction, as if four hydrogen nuclei coming together, fusing together, and produce a helium nucleus. Huge amount of energy is produced. As the energy tries to come out from inside, it produces a radiation pressure, a back pressure. And this radiation pressure, when it exactly balances and matches the inward force of gravity, sun being a ball of gas remains hanging there for millions of years without dissipating. And amazing, this balance of two forces is not only at the surface, starting from the center to the surface at every layer of gas, these two forces cancel out. It's an amazing phenomenon. This is called the conditions of hydrostatic equilibrium. How did the solar system happen? According to the scientists, this huge cloud of gas and dust which was floating, it had a small spin. So because of self-gravity, as it was becoming smaller and smaller, it never became a small sphere. It condensed into a disk because of conservation of angular momentum. At the central part of the disk, when the temperature rose to 1.5 crore degrees centigrade, sun was born. In the outer periphery, where the temperature was less, gas and dust condensed, coagulated, coalesced, and has given birth to our planetary systems. If I bring down the sun from the sky, cut it like a watermelon, inside there are three regions. The very central part where the thermonuclear fusion reaction is going on is called the core. Then the energy that is generated in the core, for a huge volume, it freely flows. It's called the radiative zone. And the sun is very funny looking. From the surface up to a depth of 650 to 700 kilometers, columns of gas, pillars of gas stacked one after another. Heat comes from inside, hits the bottom layer of the gas pillar. Gas, when it is heated, rises up, comes to the surface, deposits the heat as sunlight, and becoming cold like a fountain, goes down and continuously raises the heat from inside. This is called the convective zone. Outwardly, sun is again divided into three regions. The sun that they get to see in the early morning or evening is called the photosphere, the sphere of light. Over the photosphere of light, in a very thin layer, exquisitely pink-colored gas can be seen, and that is called the chromosphere. Chroma means color. And for thousands and thousands of kilometers, milky white radiation called corona. The word corona comes from Latin. It means crown. Nothing to do with, obviously, the coronavirus. This is on the left-hand side, I think in your case it will be the right-hand side, you can see the photosphere, the actual picture, granulations. But if you see deeply, it is like a beehives, right? Each cell is actually a pillar, a column of gas. As the heat is coming through the middle of the cell, it is lighted up. But the moment it comes on the surface, deposits the heat as sunlight, like a fountain going down. Because the heat is missing, it is typically dark in color. Each of these cells may look small on the surface of the sun, but on an average, their size is 950 to 1,000 kilometers in diameter. And then you can see on the lower part, the chromosphere. During a total solar eclipse, the exquisitely pink-colored spicules of gas reaching out in space, they actually transport the magnetic energy of the sun and deposits that energy 1,000 kilometers away from the surface. Thereby, amazingly, though the surface temperature of sun is around 5,600 degrees centigrade, but the temperatures at some parts of the corona can reach up to 2 to 3 million degrees centigrade. This is one of the most beautiful pictures of nature. Yes, a solar eclipse and the corona coming out. Absolute beauty. If after studying a sun, one young student is interested into doing something about the sun, I think there are very simple, basic 4 equations of mass conservation, hydrostatic equilibrium, energy transport, and energy generation. But I'm sorry to say they cannot be solved, directly. Because of the critical boundary conditions, you have to do an iterative method, and as a result, you have to put it into a computer, churn out the computer and churn out the numbers, and can get a model of the sun. So what I spoke about is not just somebody has actually stuck a probe inside the sun and found out about it. It is rather a model calculation that has enabled the scientists to talk about the deep inside of the sun. Suns sometimes become active. Sometimes you get to see black splotches on the surface of the sun, sometimes one, sometimes 10, 20 in a group. They're called sunspots. What are they? The surface temperature of sun is around 5,600 degrees centigrade. At that temperature, no gas can remain as gas. It becomes what is known as plasma. And plasma has a property, wherever there is a magnetic field, it will try to get deflected from the magnetic region. And that is the reason on the surface of the sun, very randomly small pockets of magnetism to form. A column of plasma from inside, as it's trying to bring the heat out, if it realizes that over it, there is a magnetic field, it will not come out straight. It will take the heat away from different directions. No heat comes out from that region. It will be cold and it will look dark. So typically, sunspots are signatures of magnetic activity on the surface of the sun. This is an amazing picture taken in 2012 by Solar Dynamical Observatory, operated by NASA. And here, the sun really doesn't look like a smooth egg yolk as it appears to our eyes in early morning or evening. Tremendous amount of explosions are happening on the surface of the sun every second. Thousands of tons of gas are getting thrown up to a height of 25, 30,000 kilometers, making beautiful arch and loops falling back onto the surface. Sometimes they get thrown up with such a force, they get detached from the surface of the sun and flow past the whole solar system as a solar wind and sometimes solar storm, right? See this beautiful picture taken in 2015, right? A beautiful arch, a loop of this hot plasma getting thrown up and falling back onto the surface. You know the size of the cavity. The cavity is so large, 3 Earths can go side by side inside this cavity. That's an amazing phenomenon. And I spoke about this charged particle. I spoke about the speed and momentum. So why we're alive? How is Earth so secure for life to happen? Because by chance happening, by accident, Earth behaves like a bar magnet. Around the Earth, like the peels of an orange, there is an invisible magnetic shield. These charged particles, they come and slam onto the magnetic shield, cannot enter, flow past the Earth, and we think we are the king and queen of ourselves. But if you remember your class 7, 8 days of drawing the magnetic lines of force of a bar magnet, in the north and south magnetic polar region, there are open field lines. These charged particles, they get reconnected through these open field lines and enter the polar region of the Earth. Before hitting the ground and creating all the destruction, they actually interact with the air molecules and make the air glow. And what you get to see? Aurora Borealis in northern hemisphere, Aurora Australis in southern hemisphere. I was very lucky in around 2005, in the northernmost part of Norway, a small camera with a friend, I could take this beautiful photograph, and it reminded us that though we think sun, taken for granted, every morning coming up, evening going down, tomorrow again comes up, but every second sun is interacting with our Earth, every second of our existence. And a little bit this way, that way, believe me, my friend, We have to just raise our hands and wait for things to happen. And because of this huge amount of interaction in the space weather, it is now imperative for the human civilization to progress and proceed to know about the effect of this solar radiation. And you all know about the Parker Solar Probe. A couple of years back, it was sent to go very near the sun and study the atmosphere of the sun. The solar system, how did it happen? As I mentioned, I hinted at you that when 460 crore years back from the disk of gas and dust at the central part, the sun was born. At the outer periphery, when the temperature was less, gas and dust condensed, coagulated, collided, and ultimately gave birth to very hot spherical objects. For millions of years, they dissipated away the heat, and at least the first four, Mercury, Venus, Earth, Mars, became rocky and terrestrial, whereas the other four, Jupiter, Saturn, Uranus, and Neptune, are mostly made up of gas. This is a fantastic collage of all true color pictures of planets. Mercury, Venus, covered by haze of clouds made of sulfuric acid, atmosphere 96.5% carbon dioxide, thus average surface temperature is 464 degrees centigrade. Our Earth, amazingly, Mars, red in color because covered by ferrous and ferric oxide. And this 2001 photograph taken by Hubble Space Telescope has excited the scientists because in the polar region, they have found white sediments. And according to them, this white sediment is a mixture of water ice, dry ice, that is carbon dioxide ice, and maybe ammonia ice. And according to them, even if a part of his water ice, maybe liquid water, is to flow on the surface of Mars, and on Earth, every drop of liquid water is synonymous with life. So was there life on Mars? Is there still life on Mars? Big question. Jupiter, the biggest planet, 319 times heavier than Earth, takes 12.86 years to go around the sun, but takes only 10 hours to go around itself. And with that tremendous spin, it has dragged the clouds of the atmosphere and created this elastic belt-like structure. The most beautiful planet, Saturn. Beautiful ring system, lakhs of kilometers wide, only 1 to 100 kilometers in thickness, right? But it takes 29.4 years to go around the sun. Uranus with a ring, yes. All the extra planets, the exterior planets, Jupiter, Saturn, Uranus, and Neptune have been found with rings. Mars is of special importance because, my friends, the students, for the last 10, 15 years, almost every 2-3 months, you get to talk about Mars, either in newspaper or television channels. Why? Because of these sort of features that has been discovered. As if liquid water has flown to the surface of Mars billions of years back. So when Phoenix landed in 2008, one of the first experiments it did, and it scratched a little bit, we found the whitest sediments. Scientists realized you see these 3 white pebbles here after 4 days not to be found. This is probably for the first time proof of water ice was found outside the boundary of Earth. And this picture is amazing. It is not yet very much public because of the secrecy, but you see, this is the sidewall of a crater on Mars. During summer, you see the black fingers, and during winter, not there. Scientists found out liquid water was floating on the surface of Mars. Very brine, it's almost brine, very salty, but still liquid water. That is the reason in 2012, 6th of August, when Curiosity landed onto Mars and started sending photographs, dried up riverine beds, pebbles which can only occur when big stones floating through water, get smashed up, become small, and become smooth, which we see on Earth. So definitely, these are definite indications of hint of water on the surface of Mars. And in that case, I should mention today also, that is 2014, it's an amazing thing that happened to every Indian and to global scientific community, Mangalyaan, right? On 24th September 2014, almost 6 years back, at 8:02 a.m., Mars Orbiter mission successfully entered the Martian orbit, and still today it is sending data. Amazing amount of tremendously high resolution data of Mars and its surface. Even the NASA scientists have applauded the ISRO scientists for creating such a fantastic camera which can take pictures from 2-dimensional photography. They are creating 3-dimensional topography. You can imagine the resolution. Amazing. And only just day before yesterday, on Monday, we came to know that scientists have discovered phosphine molecules in the atmosphere of Venus. And we all know that phosphine can only occur if there is a biological cycle going on in that place, right? On Earth, it is very difficult to find in places where there is oxygen. But Venus, I told you, 96.5% is carbon dioxide atmosphere. Clouds are made up of sulfuric acid. But at the higher levels of the atmosphere, where the temperature is a little less, they have found phosphine. And now, a new branch of interest in Venus and whether there was or is still life on Venus. Then comes asteroids. 1801, Giuseppe Piazzi, an Italian astronomer, discovered a piece of rock typically 900 kilometers in diameter between the orbit of Mars and Jupiter, named it Ceres. People thought a new planet has been discovered. But within a couple of years, three more, Pallas, Vesta, and Juno, each around 500 kilometers in diameter, was discovered in the same region going around the sun. Scientists realized a new class of object is getting discovered. And starting from 1801 till today, thousands and thousands pieces of rock, 10, 20, 150 kilometers in size, have been discovered between the region, between the orbit of Mars and Jupiter, all going around the sun. They're called asteroids. But these asteroids are very special because why? Though we say that our solar system is defined by the 9 planets, but we forget thousands and thousands pieces of rock are also going around the sun. In this representation from NASA, each green dot is a discovered asteroid, and each red dot is also a discovered Apollo asteroid. What is the speciality? Their orbits intersects the orbit of Earth. That means the Earth is going around the sun on its own. One of these objects can come and hit the Earth any point of time. If that occurs, believe me, my friend, anything can happen. The level of destruction is totally undefined. And if you ask me, when can this happen? Believe me, my friend, any point of time, right? Though there is tremendous amount of research and observations going on in identifying each object which can come on an Earth-crossing maneuver or orbit, but still, surprises do occur. And that is the reason scientists all over the world is trying to formulate paradigms whereby if they find a meteorite is coming or an asteroid coming towards the Earth, which can cause destruction, how to mitigate that problem, either by sending a rocket with an atom bomb or using huge masses, spacecrafts to deflect the object called gravity tractors, or to attach a cell which will, by use of the solar wind, can be deviated from its path of collision with the Earth. At exciting times, a couple of years back, a Japanese spacecraft called Hayabusa landed on an asteroid called Ryugu, and the first photograph of a close-up of the surface of an asteroid. And they have found huge amount of mineral deposits. So asteroids are not only the objects for destruction, they can be also used for the betterment of the human civilization if we can somehow mine those minerals. Comets, what are they? 460 crore years back, when from the disk of gas and dust, our sun was getting born in the outer periphery, where the temperature was less, right? Huge chunks of ice, water ice, dry ice, ammonia ice were floating around. When their typical size became 15 to 20 kilometers in diameter, they also started going around the sun in extremely elliptical orbit. In their elliptical orbit, as they came close to the sun, by the sun's heat, the ice melted and created million kilometers long tails. There are two tails. One is a dust tail and one is an ionic tail. So a comet, which is a spectacular sight, right? But is actually the head is 10 to 15 kilometers in diameter. We all know that starting from 2003, there was a tremendous debate of whether we have 9 planets in the solar system. Because in the 16th November 2003, this new object was discovered in the far-flung reaches of the solar system. Initially, the name was 2003 UB313. Now the official name is Eris. It was larger than Pluto. Its orbit was such it will take 557 years to go around the sun once. So the people started asking, if Pluto is a planet, why can't you call this object a planet? And after a tremendous amount of deliberations at the 26th General Assembly of the International Astronomical Union, and ultimately, believe me, my friends, through voting, it was decided to create a new structure of the planet of the solar system. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, these will be called classical planets. And a new class of objects were nomenclatured. They were called dwarf planets. And our Pluto, the largest asteroid, Ceres, and Eris, this newly discovered thing, became dwarf planets. Only in 2015, 2 more has been incorporated, officially recognized as dwarf planets. They're called Haumea and Makemake. So forever, the definition of the solar system was changed. It was NASA in the last decade who started a slogan, follow the water. Try to find liquid water outside the boundary of Earth. Mars, yes, maybe. Any other place? Yes, they now know that Europa and Enceladus, both of them, has a tremendous reservoir of huge liquid warm water beneath that 10 to 15 kilometers thick water ice crust. And so they are planning to send 2 spacecraft in 2024, which will land on 2029, at 2029 on this, create a huge drilling system, and ultimately touch the water and start taking photographs and information and send it back. So maybe another 10 years we'll come to know life is not particular to Earth. Life is everywhere. It is universal. We haven't found it. It is now, my friend, in this coming some time to take you out of the solar system. If I take you out of the solar system, the sky is amazing. As if each corner, each dot in the sky is a star and a huge gas cloud. Why we can't see it? Because the problem is with the human eye. Human eye has something called perception of vision. Within 1/10 of a second, whatever amount of light enters through our eyes, enters the pupil, falls on the retina, the optical nerve immediately takes them to the back of our head to create an optical image. Our eyes cannot integrate light like a CCD chip. If our eyes were like a CCD camera looking in a particular direction in the sky for 10, 15, 20, 30 hours, you would have seen each dot in the sky is made up of a star. And huge gas clouds of all hues, colors, saturations. Are all the stars like sun? Answer is yes and no. Why yes? Because most of the stars, around 91 to 92% of the stars, are burning hydrogen to helium at their core. Why no? Because the stars can come with a very different initial masses, surface temperature, and chemical composition. Stars come with varying masses, 0.08 to 100 times the solar mass, right? Why this limit? Because 0.08 less than that, the gravitational pressure is not enough to reach that temperature to have hydrogen accretion. And more than 100 times, the gravity becomes so more that whatever happens in the inside, gravity takes over. What is solar mass? 2 into 10 to the power 30 kilograms per, right? And it is not just the 4 hydrogen nuclei, 4 protons fusing together to produce a helium. In case of sun, which is called the proton-proton chain reaction, 2 protons giving rise to basically a deuterium and neutrino and other basic radiation and particles. And then a deuterium with a helium, with a proton creates 3 helium, and 2 3 heliums creates a 4, 2 3 heliums creates a 4 helium and 2 protons. So effectively 4 hydrogen nuclei, 4 protons creates some helium, right? But this can also, in heavier mass stars, another thing happens called CNO cycle, carbon, nitrogen, oxygen cycle. Though in nuclear physics, there is nothing called a catalyst, but like, similar to a chemical reaction, 12 carbon nucleus plays a role of like a catalyst. And one after another, protons interact with the nuclei, producing carbon, nitrogen, and then again decaying and forming carbon, nitrogen, oxygen, and ultimately gives rise to 4 helium and 12 carbon. So 12 carbon as it remains as 12 carbon and 4 helium forms. In terms of surface temperature, stars can come in different ranges. The surface temperature can be 50,000 degrees centigrade and as small as 1800 degrees centigrade. And it was almost a century and 20 years back, quite a number of scientists and obviously a lady, Mary Jum Cannon, at Harvard Smithsonian Astrophysical Observatory created a classification scheme. The hottest surface temperature, let us call it O star, next hot, B star, A star, F star, G star, K star, and M star. Sun with a surface temperature of 5,600 degrees centigrade, though to us it is very special. But in the whole scheme of events, it's a very mundane, very ordinary, normal G-type of star. This classification of O, B, A, F, G, K, M is not only on the basis of the surface temperature, they're on the basis of the characteristics of the spectra emitted by each of the stars. Because low mass stars or even low surface temperature stars, they will have certain specific signatures of atoms and molecules in the spectra, whereas hot stars have different signatures. So just to give you an idea, this spectra, it looks like very innocuous. Each spectra can have 22,000 lines and upwards. So it's a back-breaking job for any astronomer, astrophysicist, or a budding research scholar to understand even each single star. Because it is only the signal of light that comes from the stars to us. We cannot bring it to our lab, cut it open, put chemical, test it, smell it, and say, aha, this is this. So the single signal of light, the electromagnetic radiation, you have to massage that and bring out all the data, all the information that you can get to know about these celestial objects. And later on, since the classification scheme was so robust, it was found if any physical properties, mass, color, birth, death, evolution, composition, stars can be divided into O star, B star, A star, F star, G star, K star, and M star. That brings me to the question of life and death of stars. Stars, where from they arrive? Stars are actually born from interstellar clouds of gas and dust. In the sky, there are regions where one can see these clouds and also star formation processes, though we cannot see them because of the deficiency of our human eye. Just to give you an idea of how beautiful the interstellar clouds can be. True color pictures, right? 1,000 solar system will be born out of it. See for yourself. But you have to, if you take up astrophysics, you have to understand them. For example, the greenish blue color in the top, oxygen 5, oxygen 6. The bluish color in the middle, it is actually neutral hydrogen, sulfur, sorry. Then there is zinc or molybdenum on the green, and black is iron, or is white is titanium. 2.5 million pixels in this photograph. A photograph can produce 10 to 12 PhDs. It's a tremendously backbreaking job for astrophysics. And see this. I think this takes the cake. Amazing. See the structure. You see what is the size. You see these small nodules here. You know the size of each of the nodules. Each nodule inside has a fully formed solar system-like object. So imagine the size. So the universe is throwing a challenge to our human intellect. You want to know. You think you are clever. Try to understand me. Right? So it is such a fascinating challenge, journey to go deep into space. And obviously, the stellar nurseries at the tip of this dust clouds or columns of dust, so that they look dark because they're absorbing light. As they're moving the tremendous speed through the interstellar medium, because of the tremendous ram pressure created at the tip, new stars are getting born regularly. What an amazing sight. If you are born, you have to die. Because interstellar clouds, by the way, is not just, vacuum. Huge amount of material. The chemistry is amazing. I'll come to that. Stars die in different ways depending upon their masses. Stars with initial mass 1 to 8 times the solar mass, how do they end their life? Let us take the example of sun. Sun is burning hydrogen to helium at the center. For how long? The amount of hydrogen that is remaining in the core region, scientists have done a calculation, for roughly around 500 crore years or 5 billion years, sun will be burning hydrogen to helium at the core. When all the hydrogen get transformed to helium, the thermonuclear fusion reaction will stop. The energy production will stop. The outward pressure will stop, but gravity is there. The sun will initially start becoming smaller. As it is becoming smaller in the peripheral region, in the outer envelope region, because of the constriction, huge amount of temperature will rise. And that temperature, when it reaches 1.5 crore degrees centigrade, 4 hydrogen nuclei will fuse to give rise to helium. So the reaction that was happening at the core will start happening near the surface. And because of this reaction, huge amount of energy will be produced as the gas when heated, as it expands. So sun will start becoming bigger and bigger. When sun is becoming bigger at the central region, the helium core, because of gravitational contraction, the temperature will rise to 10 crore degrees centigrade, which is enough to burn 3 helium nuclei to produce a 12 carbon. Two helium nuclei fuses to give you a beryllium. 1 beryllium with another carbon gives you another helium gives you a carbon. Again, heat will be produced. The inside will stop becoming smaller. But by that time, the outside has become so big, it will be called a red giant star. Through small calculation, it can be shown after 500 crore years or so, sun will become bigger and bigger and bigger, and ultimately probably touch the orbit of Earth. Mercury, Venus, Earth will all cease to exist, will all go inside the sun. And the core region, where the thermonuclear fusion reaction of helium to carbon starts, the central part becomes tremendously bright, white dwarf. Over millions of years, the exterior, the envelope ultimately dissipates in the atmosphere, creating a cloud-like structure called planetary nebula. The word nebula means cloud, and the inside will be a white dwarf. For millions of years, this white dwarf will continuously dissipate the heat. But since no heat generation happening after the carbon formation, it will slowly become very cold and dark and ultimately called brown or black dwarf. We'll never be able to see it. But that's not the end probably. Some of the astronomers have hinted at a fantastic end for stars like our sun. Inside the Earth, under tremendous amount of temperature and pressure, carbon gets transformed to diamond. So you can expect 10 to 15 kilometer piece of diamond floating in the sky. Nobody knows. And this planetary nebula are wonderful subject of research, because it was almost 20-25 years back we realized that it is pulsating. The star starts pulsating, and at that time it is called a variable star, and gives out shells of material. And each shell, we found out, me and my group, that is propagating with a tremendous speed of sometimes Mach 2 to Mach 8. Mach is the velocity of sound. Thereby, and behind the shock front, due to adiabatic cooling process, huge amount of chemistry goes on. And believe me, my friend, it was almost 25 years back, we ultimately realized that these sort of shocks can produce tremendous amount of chemistry, right? And we have found huge amount of rich elements, organic elements, into this whole pulsating phenomena of stars. These are the molecules that has been, we produced it in the computer, but luckily they were also observed, right, by ISO spacecraft sent by Holland. And that tells us every star at its end phase produces the prebiotic material of life to happen. And regarding the white dwarf, I just wanted to mention that white dwarf cannot be of any mass. It was almost a century back, almost, not really a century, 85 years back, that Subramaniam Chandrasekhar told us that there should be a limit to the mass of a compact object like a white dwarf, and that limit is 1.44 solar mass, right? And he got the Nobel Prize for it, definitely. Stars whose initial mass is 8 to 25 times the mass of sun, how do they die? Inside them, hydrogen to helium, helium to carbon. But since the mass is more, the gravitational pressure is more, the temperature is more at the core generated. So one after another element starts getting fused and produced. Hydrogen, helium, carbon, oxygen, neon, magnesium, silicon, and then ultimately iron. Since iron has the highest binding energy, you cannot produce pressure and temperature to fuse iron nuclei. So the inside, the core of the star takes a shape of a peels of an onion. Layers of hydrogen, helium, carbon, oxygen, neon, and so on and so forth, inside a solid ball of iron. When this happens, the thermonuclear fusion reaction stops, but because of gravity, because of the pressure, all these layers starts producing tremendous amount of pressure. The poor iron center becomes incompressible. And ultimately, as they rush towards the center, all these layers, they get almost a kick, a recoil, and there is some sort of an implosion, though it is called a supernova explosion. Huge amount of energy comes out, 10 to the power, on an average, 10 to the power 54 arcs per second. And at this point of this explosion, the temperature reaches so high that starting from 56 in the periodic table, iron, all the other elements gets produced in a fraction of a second. Since they cannot be produced in huge quantities, because for a small time they are produced, they're called, on Earth, they are called rare earth elements. And this process is basically called the S process of nucleosynthesis that produces this. And that has made us realize that each atom of iron in our blood, each atom of calcium in our bones, the origin lies in such an explosive event. And we are all star children. In case of the mass of an object that remains behind, which ultimately you all know can be called neutron star, and ultimately a rotating neutron star can produce a fantastic physical phenomena called pulsar, which Professor Bhattacharya probably will touch upon, right? It is one of his, he's a world expert in this. So basically there is also a mass limit called Tolman-Oppenheimer-Volkoff equation giving rise to this mass limit. And this neutron stars with intense magnetic field producing bright pulses Professor Paul mentioned about the pulsars that OT radio telescope had discovered, and it was the beginning of this thing. But just to give you an idea, in both these cases of death of stars, low mass and medium mass, ultimately it starts from a gas cloud and ends again into a gas cloud, but much more enriched. And out of this concept, we ultimately have realized, starting from only except hydrogen and helium and synthetically produced elements, all the elements that we get in the universe have been produced in astrophysical phenomena. Hydrogen and helium, as professed, probably was born at the very birth moment of our universe itself, but all other are astrophysical. And this tremendous amount of mixture of chemistry in the life cycles of gas and dust that happens in the space has given rise to this concept in the recent time that if somebody asks where from life has come, the answer is the first prebiotic genetic material of life probably came from space. Through a collision of a meteorite, a comet, an asteroid, which destroyed a lot of things, but at the same time seeded the earth with the prebiotic material, which through the Earth's atmosphere, environment, temperature, ultimately life sprung out of it. And a new, absolutely fantastic subject of astrobiology has become very important. So you think astrophysics, astrochemistry, astrobiology, astrostatistics, astromathematics, astrocomputing. What else can you expect from a subject? So it's a tremendous, this introduction tells you, it's a most vibrant, most challenging, and most amazing subject that a learned mind can think of getting into. And obviously, in the later part of this seminar, you'll be hearing about the cosmos, right? But just to give you, as this small cartoon tells you, it's a tough time for a scientific researcher doing models of stellar evolution. You know, it's almost banging your head. But ultimately, if you get the success, it's an amazing feeling. But there are death of stars of mysterious kinds. And stars with initial mass of 25 times or more the sun's mass, we all know they condense, contract, and ultimately become almost an extremely dense point where gravity is so strong that nothing, no particles or even electromagnetic radiation can escape from it. A singularity, and it's called a black hole. And this can be understood on the formulation prescription of the beautiful theory given by this amazing person, Albert Einstein, through his general theory of relativity. The equation here looks so nice, so elegant, so simple, but there is tremendous amount of complexity in that. Basically, it is the nature of gravity, mass, which can produce a curvature in space and time. And this curvature can be looked up, can be envisaged as if the gravitational effect of an object. Gravity is not a force in that sense. And in that, if you have a singular point of tremendous density, as if there will be some sort of a dent, right? As if there is some sort of a tunneling effect, or almost, going a funnel going down to almost infinite depth. The singularity can be termed as the presence of a black hole. And there is a region where if you cross that boundary, you can never come back to real world. So the concept of event horizon, right? Here you see the black disk at the central part. Yes, you cannot see a black hole, but you can see the event horizon. But scientists realize that if there is a star nearby, that the black hole will try to attract the material from the star, and the material, as it's going round and round with tremendous speed by friction or other physical properties, it will start glowing in X-rays, right? So you get to see an accretion disk, and some material, because of the magnetic activity, will get thrown up perpendicularly as jets from two polar regions, giving rise to a searchlight kind of thing. We haven't found a stellar black hole, at least a picture of a stellar black hole. But only a couple of years back, you all know, this is not a picture, this is actually taken from a movie, that how should a supermassive black hole, which is professed to be part of the central part of some massive galaxies called active galactic nuclei, how they will look, their accretion disk will look like this. The upper part, you see this curvature. This is because of the gravitational lensing effect. You are seeing the other side of the accretion disk, and lo and behold, this was discovered. The shadow of darkness right? What is called the photograph of darkness. And then the picture goes on. Another 3-4 minutes for me. We all know that all these stars, all these supernovae, all these white dwarfs that we are talking about is part of a huge system called Milky Way galaxy. Almost 20,000 crore stars, 1 lakh light year across, right? It's a huge thing. And our sun is not just at the center of everything. Don't think yourself so important. 28,000 light years away from the central part of the sun, and our solar system is going around the galaxy at 220 kilometers per second. Think of the speed, amazing. Till now, after the birth, around 20 times sun has gone around the central part of the galaxy. And then we go to the local group, where around 40 galaxies, typically 40 galaxies, clustering around each other. There are 3 major spiral galaxies, our Milky Way, Andromeda, and Triangulum. And most of them are either irregular or dwarf spheroidal galaxies, right? The closest one, obviously, is called the LMC, Large Magellanic Cloud. But only 10 years back, we have realized the closest galaxy is called SAGDIG, Sagittarius Dwarf Elliptical Galaxy, which is only 50,000 light years from the central region. Amazing, right? And then, as we go in the hierarchical structure, you'll see, starting from Earth and Moon, our solar system, outside our solar system, different close stars around the solar system, in our galaxy local group, then clusters of galaxies, super clusters. And when you go to the whole picture of the universe, it looks like grains of sand. As if in the dark depth of space and time, each entity now here is a collection of 10,000, 20,000, 5,000 crore stars, a galaxy. Huge amount of gas as well. And then probably today, you will come to know the most exciting esoteric concept of how our universe was born. 1,372 crore years back, as if from a dense point, from a singularity, it was the beginning of space and time, the origin of matter and universe, energy, right? The Big Bang hypothesis. A lot of people ask the question, what was before that? Where did that thing happen? And that has given rise to enormous number of theoretical understanding research, which you'll probably get to hear from other eminent distinguished speakers. But the Big Bang model has survived because the prescription that it has given has been proven that the abundance of light elements at the early moments of formation, space filled with a radiation, which today is in the microwave region with a typical temperature of 2.7 Kelvin, and galaxies still today are going away from each other as if an expansion is happening. And this expanding universe concept is still the most subscribed and prescribed concept. And the fascinating aspect of the microwave radiation, the background radiation, right? It has been observed with minutest details. And India has taken a very leading role, at least from the theoretical aspect and now recently from the technical aspect also, to understand, because each of these fluctuations in this microwave background, right, 1 in 10 to the power -5 in terms of Kelvin, right, is an indication of the seeds of structure formation in the universe. And that's a very big story. So when the scientists went deeper, they not only got the idea how matter was created in the very first place, which was theoretically long time back talked about, standard model. Now we know, using particle physics experiences on Earth and the observations in space, that is more or less holding still correct. But we also have come to know not everything is hunky-dory. The universe is not made up of normal matter that we experience, but the universe is made up of something very esoteric called dark energy and dark matter. Only 4% of the matter in the universe is baryonic matter, is this normal matter that you and I are made up of. There are other objects called dark matter, particles, which a lot of theoretical understanding is there, but no practical discoveries. And something called dark energy, it itself is an enigma. So, my friend, I'm just 2 minutes over time. I'll just finish in a minute or so. Scientists throughout the world, immense amount of interaction immense amount of intellectual interaction. They have ultimately given a more or less a standard viable prescription of how universe has evolved, how our galaxy has evolved, how stars evolve, and how probably it may end one day. But still, huge amount of things remains to be resolved, remains to be understood. And that is the hope of old people like me, that maybe these sort of seminars, these sort of concept, pictures, information will start a spark in your mind. And you will realize that in addition to all these worldly things that we are interested, there are something which are worldly, but rather universal, cosmic, cosmological in origin, which can give you tremendous amount of satisfaction if you try to understand them and ultimately give new ideas about them. So it's really a thank you from me to all of you, because it's a wonderful feeling. And I will stop the sharing just now.
So, twinkling stars or twinkling stars in the sky are the objects of wonder, interest, and query from our childhood to the present. And Professor Duwari gave a very nice and illuminating talk for all of us in this direction. You must join with me for giving thanks to him, but we will take 5 more minutes for asking question. If somebody you have, please give it in the chat box so that we can share it with Professor Duwari and he will give answer. Open. So let me ask them one question.
Yes.
So, we know that black hole is the ultimate stage of a star. Now, some people are believing that our universe may be built or our universe may be originated from a black hole. Do you agree with this?
See, first of all, to agree or disagree, I have to fully understand what is being told. In my limited intellectual capacity, sometimes it becomes defeating because I'm not actually in the subject of black holes and other things. But as I read, as a common man, you can say, there are doubts. There are sometimes, it seems that it may happen, but tremendous amount of work has still to be done, even in theoretical aspect, to give a support for these sort of theories. This is my personal feeling. And if I can get 30 seconds, I find Professor Bhattacharya has logged in. I can see him. So it's really, as I mentioned in my Facebook post, it's an honor for me. It's a privilege for me. Because as I told you, 30 years back, he was the person who first pointed fingers to me and said, do this, do that. And that started the whole journey for me, at least. Thank you to
nice opportunity for all of us.
Nice to see you, David.
Thank you. Okay.
So if there is no other question, we must thank again to Professor Duwari for giving his valuable time with us. And we hope that he will come again to North Bengal University for giving talk in the campus. Yes. Okay. Okay. Yes, he asked that how did they extract such a signal from a huge background, and how did they associate the signal with the stated galaxy only out of many?
Oh, I think Professor Kanak Shah will be the best person to answer this, but I know that huge amount of software manipulations using almost all knowledges about statistical analysis, mathematical analysis, computational power is used to take out the actual signal from the disturbing background noises, colored noise and other things from interferences. That itself is an industry. In fact, IUCAA, initially, when I was there, one of the main activities was how to dredge out gravitational wave signals out of the tremendous amount of noise. You have to achieve a superfine level of 10 to the power minus 19, 10 to the power minus 20, right? But it can be done, and it has been done in LIGO. So similarly in other, that was in gravity waves, but in electromagnetic radiation also, huge amount of filtering techniques, not only material, but software level filtering techniques are used to take out the signal.
There is one question more from Sam Dash. He asked that Professor Kanak Shah once told us that the collision probability of Earth and others is almost zero. But how asteroid may hit us?
See, the point is that Earth and other planets, that may be almost zero. But believe me, my friend, asteroids or even meteorites, they regularly hit the Earth. Though they are small, but almost every day, every year, thousands and thousands micrometeorites, small things, they come and hit the Earth. So that you cannot stop. But big bodies, yes. But nobody can say that tomorrow Jupiter is coming and going to hit the Earth. That is absurd. I mean, it cannot happen. But celestial objects do hit the Earth. If they are big, then that is a cause of problem.
Okay. Just one question. Just one question.
Okay. The answer is that, as far as my understanding, the side of the Earth facing the moon, the gravitational attraction of the moon on the water surface is more than the centrifugal force that the surface water feels. And that's the reason the water bulges in towards the moon. 180 degrees away, it is now the centrifugal force which is much more dominant over the gravitational attraction. And that's, as a result, water bulges in this direction in a very short way, though there are details of it. A very basic question, a lot of people ask me this. I have to answer this by asking a question. How come your local diagnostic lab tells you how much iron, calcium, magnesium, zinc you have in your blood? Tell me. What they do a spectrum analysis, right? So basically breaking up the light coming from a star or an object, you break down into its constituents wavelength and see the emission or absorption features present there. And out of that, and your CRC handbook and your knowledge, you come to know which element, which molecule, what transition causes this feature. And from there on, you slowly build up the repertoire of objects, elements, molecules, chemicals of a star.
So let us stop here because of shortage of time.
Yes.
There are many questions in the queue. So if time permits, we will send you so that we can get the answer. So we will go over to the next talk from Professor Dipankar Bhattacharya, who is a distinguished professor at IUCAA Pune. He is playing one of the leading role in AstroSat, a new multi-wavelength telescope in the sky for studying stars in the sky. So we are eager to hear from you, sir. Please.
Okay, so let me share my screen first. This here. To share the screen, I guess. Can you see this presentation?
Yes, sir.
Yes, we can see.
Okay. Yeah. Thank you very much for inviting me to this introductory seminar. Nice to interact with you, all students and participants of this workshop. Previous to this, you have heard very lucid lecture by David Prasad Dwari, who has taken you through all the way from solar system through stars to the farthest reaches of the universe. In my talk, I will concentrate on a specialized object, which he also mentioned through his lectures, and that is neutron stars. It's a fascinating object because as you will see as we go along discussing, understanding this requires all our knowledge of physics in all possible branches that you can think of. And since many of you are students of physics, I think you might find it interesting to see how different aspects of physics combine to give us a picture of this class of objects. And how a very extreme state of matter that obtains in neutron stars also tells us something more than what we can derive in the laboratory about fundamental forces themselves. So this is a real connection between the true microscopic and the macroscopic, and we will see how that connection helps us in getting a better knowledge of the universe and the forces in them. So the theme of this lecture is matter at extreme density. Let's try to get a feel for how dense can matter get. Around us, we have air. So we can ask what is the density of air, and that is about 1,000th of a gram per cubic centimeter. Then we have material in liquid state around us, water. That is sort of our unit of measure. So it's like about 1 gram per cubic centimeter. And then heaviest objects we encounter on Earth are made of heavy metals. So it can be about 20 times the density of water. In the cosmos, in astrophysical space, the range of densities you encounter is far, far greater. The diffuse gas between stars has a density of roughly only about 1 atom per cubic centimeter. And an atom has a mass of the order of 10 to the power minus 24 grams. So diffuse gas has a density of 10 to the power minus 24 grams per cubic centimeter, which is really, really diffuse, far, far less dense than the air we encounter around us. Then we go to stars. The different stars have different densities, Geisha stars. The average densities of stars range between 1/100th of a gram per cubic centimeter to 100 grams per cubic centimeter. This is the average density. Within each star, of course, the density changes a lot between the center to the surface. And then we come to planets. The planets have densities somewhere between the density of water or a little less than the density of water, because some planets are gas giants like the Saturn, Jupiter, and so on. In fact, the Saturn is less dense than water. So if you manage to bring Saturn and try to float it on water, it would float. Then the heavier planets, the rocky planets, can go up to about 10 grams per cubic centimeter, like the Earth or Mercury. Then we can go to the other extreme in the universe, where you can find objects of much, much higher density. You heard about stellar end products called white dwarfs. And white dwarfs have a density of 1 million grams per cubic centimeter. We don't have any analog in terrestrial situation of such densities. But this is not the end of it. If you have an object which could be larger than the Chandrasekhar limit of white dwarf, then gravity becomes so strong that it could condense it even more. And the densest objects we know in the universe are neutron stars. Their average densities are of the order of 10 to the power of 15 grams per cubic centimeter. Now, if you compare this with material we know, this density is like the density inside an atomic nucleus. So that is as dense as matter can get that we know in the universe. Anything denser is likely to form a black hole. So what's the distinctive nature of these different states of matter? We know in gas, atoms and molecules are in thermal motion. So you have a container, the molecules are flying around, they can interact with the walls of the container and stay within the container. And this collision between the containing walls and the gas particles provides a force on the sides, and that's what we call pressure. So that's the origin of thermal pressure of gas. So any imaginary surface that you can put within this gas volume will experience a pressure because of collision with the gas molecules. In liquid state, the interparticle forces become important, and the particles cannot move freely by themselves anymore without regard to other particles. And the Coulomb interaction between individual particles holds them together and restrict their motion. And however, they still have a considerable amount of random motion, and the material can take any form where we put in. So this is flexible, and the interactions are important but not overwhelming. When you go to solid, then the interactions become even stronger, and this stronger interaction imposes a certain order on the material. For example, the ions can arrange themselves in a crystal order, while the electrons, some of the electrons may be free and permeate this whole crystal. So this kind of material, let's say liquid or solid, they are held together by electrical forces. The size and shape of an object is determined by a balance between attraction and repulsion. So there's attraction between unlike charges and repulsion between like charges. And that decides what kind of density this material will achieve. Now, what happens if we try to get denser? So how do we get denser? We need to apply a squeeze to this material. So if I apply a squeeze to, let us say, a solid, the first thing that will happen is it will strip off electrons from atoms. So material will get ionized, it will start reaching a plasma state. And under the influence of external forces, whatever is causing this material to be squeezed, ions can now start getting closer. The density will rise until Coulomb repulsion will balance the external force. So what is the kind of squeezing force that can be applied from outside, can cause this kind of change of state of material? A natural source of external squeezing force is gravity. So Coulomb forces balancing gravity is a natural occurrence in the Earth, for example. So Earth is an object in equilibrium where gravity is trying to squeeze the whole Earth to a point because it attracts every bit of the Earth, attracts every other bit and try to come closer. However, the Coulomb force of the material which makes up the Earth is repulsive and it is resisting this squeeze. And that is how the Earth is in equilibrium. So all planets and moons that we know have Coulomb forces balancing gravity. However, if more and more matter is added, gravity will eventually overcome the Coulomb force. So what will happen then? This is the reason why the planets cannot get heavier than about Jupiter. So Jupiter is about the largest or heaviest planet. Maybe a few times Jupiter is the heaviest planet that can exist. Beyond that, Coulomb forces balancing gravity is no longer possible. Now stars too are held together by gravity. The stars are much heavier. So there, the Coulomb forces are not sufficient. They're much heavier than planets. So the opposition to gravity there comes from thermal pressure of gas. And if the thermal pressure of gas has to oppose gravity, then obviously the gas has to be very hot. And the gas gets so hot at the center of the stars that nuclear fusion can occur. And this nuclear fusion then supplies thermal energy, and this thermal energy keeps the gas hot. If the nuclear fusion was not there, then the thermal energy will be lost because the stars are embedded in cold outer space, radiation leaks out, and then radiation carries away the internal thermal energy. So to keep it hot, you need nuclear fusion. Eventually, of course, the nuclear fuel will run out and gravity will win over thermal pressure. And in the previous talk, you heard the different possible outcomes that happen when such a thing occurs. So the stellar core will collapse because it is no longer producing any energy. Coulomb forces, of course, are inadequate to provide support because these are much heavier than planets. So the matter will continue to get much denser once the thermal pressure support is lifted. So what happens when you take this material and make it much denser? You will encounter a new type of pressure, which is called degeneracy pressure, which we normally do not come across in terrestrial material. They do exist, but pressures of other kinds are much stronger compared to degeneracy pressure in terrestrial material. So therefore, we don't talk about it. But when you squeeze material to such high densities, degeneracy pressure may become the primary source of pressure. So what is degeneracy pressure? So let's talk about electrons. So electrons are elementary particles with half integral spin, with spin angular momentum of h cross by 2. And we know that such particles obey Fermi-Dirac statistics. And that leads to Pauli's exclusion principle. The Pauli's exclusion principle tells us that not more than one particle obeying Fermi-Dirac statistics can occupy a specific quantum state. Now, if we consider free electrons, so free electrons are moving around in free space, and let's say we contain them within a volume, then we take the position space and momentum space and create a 6-dimensional space. We call it phase space. All of you who would have studied statistical physics would be aware of this. The phase space combines the 3-dimensional positions and 3-dimensional momenta. And in this phase space, we can construct individual quantum states. Individual quantum states have a volume of h cubed. So you can divide the entire phase space into individual quantum cells of volume h cubed. And there is only one particle obeying Fermi-Dirac statistics which is allowed to occupy any one of these quantum cells. However, these particles also carry spin. And since the spin can be either up or down, so that brings in an extra degree of freedom in quantum states. So in each of these phase space volumes of h cubed, you can put 2 electrons, one with an up spin, one with a down spin. So each cell may contain therefore at most 2 electrons of opposite spin. Now I am drawing here a one-dimensional reduction of this phase space where there is one position and one momentum, x and px. And I have drawn some quantum states over here. Each of these squares correspond to one phase space cell. And in each of these phase space cells, we can place 2 electrons. So now suppose I have a certain number of electrons as shown in this diagram. Now as you can see, since my box is only this big, the electrons can occupy the lowest momentum state only until this is filled. After that, there are no more states available because we have restricted the volume over here. So any more electron that you want to put in will then have to go to the next higher momentum state. So you can get a few more electrons in that momentum state. Any further electrons you want to put in this volume will have to go to a higher momentum state. So now you should realize that I have not added any temperature or anything like that over here. I'm doing this experiment at the lowest possible temperature, absolute 0. Nonetheless, because the volume is restricted and these are particles obeying Fermi-Dirac statistics, you are forced to have particles at finite momentum. And finite momentum will cause a finite pressure because it's momentum carried by particles which interact with any defined surface. So the momentum flux across a defined surface gives you the pressure. And this is going to cause you a pressure, even though the material is at absolute 0. If we squeeze this, that means if I now start taking the right boundary of x closer and closer to the origin, then obviously these electrons have nothing to, no other possibility than to go further up in momentum and so on. So the denser the material gets, the higher the momentum will rise. And therefore, the corresponding pressure will rise too. And this is the degeneracy pressure. So a quantitative measure of the degeneracy pressure can be easily obtained. We can take, let's say we have number density of electrons, the number of electrons per unit volume, let's say it is n sub e. And let's say the momentum up to which the states are filled, let's call it P sub f, or f standing for Fermi. The number of phase space cells then is 4 pi by 3 pf cubed times 1 because it's unit volume. So that's total amount of phase space volume, divided by h cubed. So that is the total number of phase space cells which are filled. And since each cell can have 2 electrons, so this must be equal to the total number of electrons in that unit volume, Ne divided by 2. And that, excuse me, immediately gives me Pf in this form, which is some constant times Planck's constant times Ne, number density of electrons to the power of 1/3. And this can then be translated to pressure. The pressure is momentum flux, which is number density of electrons times velocity. That gives you the number flux through an unit area per unit time, times the average momentum carried by these electrons. So Ne times V times P is the pressure. And since the typical P is Pf, and velocity can be given by P over me, then we can get pressure as being proportional to, this is proportional to P. So this is Ne to the power of 1/3. P is Ne to the power of 1/3, and then Ne. So that gives you Ne to the power of 5/3. However, this V equal to P over me is fine to state when the electrons are not relativistic. If the momentum becomes so high that the Fermi energy, that is kinetic energy corresponding to this momentum, is larger than the rest energy, then the velocity, while it was rising linearly with P in the beginning, it just becomes constant as the speed of light as you reach C. So for highly relativistic electrons, instead of writing V equal to P by me, we have to just put a constant value here, which is C. Then pressure is proportional to Ne to the, times the Fermi momentum, which is proportional to Ne to the power of 4/3. So you have a degeneracy pressure, which rises as number density of electrons to the power of 5/3 at lower electron densities, and then rises a little slowly as Ne to the power of 4/3 at higher densities. So let's try to draw this schematically. So if it is logarithm of density on the horizontal axis, logarithm of pressure on the vertical axis, then we have at lower densities the degeneracy pressure rising as density to the power of 5/3, and then it becomes density to the power of 4/3 at higher densities. Now, if this kind of pressure has to balance the self-gravity of an object, then we need to balance the gravitational pressure. So gravitational pressure equivalent quantity is can be roughly computed by just taking this sphere, you take an imaginary surface passing to the center, and then consider the force between the two halves, which is, let's say, gm by 2 g squared. So m by 2 is this mass of each half, and the separation between the two halves is about the radius of the object. So the g m by 2 squared by r squared is the force, and that force is distributed over this area, which is pi r squared. So dropping all the numerical constants over here, dimensionally, this is proportional to g m squared over r to the power of 4, which is proportional to g. If I write this in terms of density, then density is proportional to m by r cubed. Then this can be written as g m to the power of 2/3, rho to the power of 4/3. So if I take an object of a certain mass and either expand or squeeze it, its mass remains constant, density changes. So with the change in density, the pressure that you need to balance such a thing requires to be equal to this. So the required pressure rises as to rho to the power of 4/3. So now let's draw such a line over here for an object of given mass. So let's say I put mass equal to m1, and then I put this. So at any density, if this object needs to be balanced, then we need to supply a pressure which I can read off from this line. Now, as you can see, that such an object will intersect the degeneracy pressure line over here. So this could be an equilibrium point where the pressure required to balance against gravity equals the pressure being supplied by the material from inside, and that gives you a point of equilibrium. So this will be an equilibrium configuration. What happens if I go to a higher mass? I get another equilibrium configuration. Now, this equilibrium configuration, because the mass is higher, you need higher degeneracy pressure. So it actually finds an equilibrium at higher density. So in fact, the radius becomes smaller as you go up in mass. Unlike on the Earth, if you take a heavier iron ball, then it will be larger than a lighter iron ball. Here it is the other way around. A heavier star supported by degeneracy pressure is smaller in size than a lighter star. So you can keep going up in mass. Now, since this line has a slope of 4/3, and the upper part of this curve also has a slope of 4/3, you can clearly see that there is actually a maximum possible mass which can find an intersection with this line. Beyond this, M3, there is actually no further equilibrium possible that is to be provided by degeneracy pressure. And this, in fact, is the source of Chandrasekhar limit. This mass M3, which is the highest mass that you can support using electron degeneracy pressure, is the Chandrasekhar limit. It's called the limiting mass. And given the composition of the material, which is typically helium or higher elements, this Chandrasekhar limit works out to be about 1.4 times the mass of the Sun. So if the compact star has a mass below Chandrasekhar limit, we call them white dwarfs. These are like sun-sized mass packed into Earth-sized volume. So that's how you get a density of about million per cubic centimeter. If mass exceeds Chandrasekhar limit, the electron degeneracy is no longer adequate to support gravity. So the star will then have to collapse to an even denser state. And we will see if it is even possible to support this mass as it transits to a denser state. So what happens if you take this material and start applying this gravitational squeeze? We already said that electrons, because of this Pauli's exclusion principle, have acquired Fermi momenta, which means each electron has acquired a kinetic energy. As you get denser and denser, the Fermi momentum, of course, rises and the kinetic energy rises. Already when the electron has become relativistic, the kinetic energy has reached the rest mass energy or above of electrons. But you can squeeze it further, and electrons' Fermi energy, as shown in this diagram, will keep going up as you go to higher and higher dense state. Now, let's say you consider a terrestrial situation and consider a neutron. The rest mass of a neutron is larger than the sum of the rest mass of a proton and an electron. So if you sum these two up, then the total energy, the total rest energy of neutron plus proton plus electron is less than the total rest energy of neutron. So a neutron can easily decay to an energetically favorable state into a proton and an electron, with the remaining energy being carried away by a neutrino. So you have the kinetic energy of the electron, proton and neutrino, plus the rest energy of these particles, giving you the total energy that the neutron started with. However, as you go to higher and higher densities, you are going to raise the energy of the electron. Remember, the difference between the rest energy of neutron and the sum of the rest energies of protons and electrons in terrestrial condition is about 1 MeV. But if you keep squeezing the electrons such that their Fermi energy rises above about 1 MeV, then when you add the total energies of a proton and an electron, then now you're in a situation where this total energy is larger than the rest mass of the neutron. So the energetically favorable things to do now is for the proton to capture the electron, make a neutron, and release a neutrino. So this is called inverse beta decay. So if you take this material that we just talked about, and since electron degeneracy is no longer sufficient to stop further collapse, so material is bound to get more and more dense, and material will go over this barrier, and it will start getting into a state where electrons and protons will combine to form neutrons until you achieve an equilibrium between the chemical potentials of these objects. So that is, chemical potential of neutron is equal to the chemical potential of electron, proton plus electron, where the chemical potential is defined as square root of pf squared c squared plus m squared c4, m being the rest mass. So this will keep on giving you a larger and larger density of neutrons as you go to higher and higher total density. So larger and larger fraction of neutrons as you go to higher and higher total densities. So this is called neutronization. So matter will get progressively neutron rich as density rises. Here is a computation of what would be the atomic number was divided by charge number at different densities if you have a fully equilibrated cold catalyzed matter. So typically on the Earth, you have material where A by Z is roughly equal to 2, or a little over. But as you go to higher densities, you can see that it is going to rise to higher and higher values. And then as you go to very high values, the nuclei will reach a situation where further neutrons cannot be held inside nuclei, and the neutrons will drop out of the nuclei and start forming a bare neutron sea. So that's called a neutron drip point. So now this neutron rich matter will exert its own pressure. Like electrons, neutrons are also Fermi particles. And as you're squeezing neutrons to highly dense state, there will be neutron degeneracy that will set in. And the neutron degeneracy pressure, the kinetic energy of neutrons, because of being degenerate, will also exert a pressure. And then as you squeeze these nucleons close together, you sample the repulsive part of the strong interaction. At larger distances, strong interaction is attractive, but if you try to squeeze them very close together, you encounter the repulsive part. And that is also going to produce a pressure which can resist gravity. So here is the potential curve of nuclear interaction. So at larger distances, you see the potential is negative, so you have an attractive potential. But then if you squeeze them to distances, internucleon distances below 1 Fermi, then you start getting this positive potential, which is repulsive part. So therefore, it resists gravity. The problem we have today is that the shape of this exact nature of this repulsive part of the potential is not known in detail. So this leads to uncertainty in the pressure-density relation that will balance gravity in such objects. So the pressure-density relation also goes by the name equation of state. So the equation of state at very high densities remain uncertain. We cannot do laboratory experiments to determine the equation of state either, because this regime of neutron star matter, which is cold and dense, cannot be probed in terrestrial experiments. We can bring matter particles very close together in colliders, but since high kinetic energies are involved in the collision, we produce material at this end in the colliders, which is high temperature and low density, relatively low density. You can bring it to quark-gluon plasma, which is high density and high temperature. Hadronic matter is sort of medium density, medium temperature. Nuclei that we know have the ideal chemical potential of about GeV. That's density of inside the nucleus is what we call nuclear saturation density rho 0 over here. They sit over here. But in neutron stars, we're talking about densities and temperatures at this end, where temperatures are very low compared to this, and it is very dense. And so far, there is no experiment in the laboratory which is able to reach this regime to probe the forces, the nature of forces in matter in that state. However, this is a fundamental physics question. How does strong interaction behave at very short distances? And this question is yet to be answered conclusively. Now, can we do this theoretically? Unfortunately, this is difficult. Typically, theoretical computations of interparticle forces, like in quantum chromodynamics, involve some kind of perturbative treatment, but the perturbative series does not converge. So for QCD, this is a difficult question to answer theoretically, completely, as you go to very high densities. Maybe over time, new techniques will emerge, which will make it possible. And experimentally, we are not able to recreate situations like the neutron star interior in terrestrial laboratories. So this remains a difficult problem to predict what kind of forces, what is the nature of the force that will obtain in cold dense material as obtained in the interiors of neutron stars. So what people do is to take the measurements we already have in a different regime and construct heuristic extrapolations to the neutron star regime. And this, of course, depends on various theoretical ideas, methods, and so on, and they lead to different predictions. So how can we resolve what is the correct description of matter at high density? Right now, we have these different possibilities based on what we know in theory as well as terrestrial experiments. So let's then talk about neutron stars and then see what kind of material and densities obtained inside the neutron star. And then we'll get back to what answers neutron stars may be able to offer. So neutron stars, if you take a typical density profile of a neutron star, you will see that the density at the surface is about 1 million grams per cubic centimeter. And that is at a distance of 10 kilometers, at a radius of about 10 kilometers, maybe 11, 12 kilometers. This is this curve is drawn for a typical assumed equation of state, where the radius is 11 kilometers, mass is 1.4 solar mass over here. So as you go from the outer region, the outer part is just full of nuclei, starts with iron nucleus at the surface and then gets to more neutron-rich nuclei as you go in. At some point, the material becomes dense enough for neutrons to fall out of the nuclei. So you have a mixture of nuclei plus free neutrons. That is called the inner crust, and that's the neutron drip point. So from neutron drip point to this point where all nuclei actually dissolve. So now no further nuclei are present. It's only a continuum of neutrons, protons, and electrons. So that happens when you reach nuclear saturation density, or rho zero. So in the crust, nuclei are present. At densities which are higher than that, which we call core, nuclei are no longer present. So it is a free mixture of neutrons, protons, and electrons. And then this density keeps rising to a few times nuclear density at the center of the neutron star. So in the core, we have roughly 90% protons and a mixture of 10% protons and electrons. But very near the center, there could be other types of exotic particles which make their appearance. We'll come to that in a moment. So the property of a neutron star, external properties, are very interesting. The radius is about of the order of 10 kilometers. It's like sun squeezed into a city. The gravity is 10 to the power of 11 times the surface gravity on Earth. The tidal force on a human, so suppose you take a human-sized person and put him on the surface of a neutron star, the difference in gravitational force between the head and the foot, which is going to try to tear you apart, that force works out to be about 1 billion kilograms. So you're going to be torn apart by a force of 1 billion kilogram if you happen to try to approach a neutron star. So please don't. In a neutron star interior, you have the crust, then you have the core, and here, indicated by this gray area with a big question mark, is the region where we find that our current knowledge does not allow us to accurately predict what is the state of material at such high densities. That's called the inner core. Now, what is the state of matter here? It is dense. And just like in solid state, which is dense material on terrestrial situation, via Coulomb interaction, you have many body effects, and you get various kinds of condensed matter properties which get generated. So too here, it is also dense. So condensed matter properties come into play, except the forces here in question are not Coulomb forces anymore, but nuclear forces. So condensed matter properties mediated by nuclear forces become important. One very interesting property is that these neutrons form Cooper pairs and form a superfluid. The free neutrons actually form a superfluid in the neutron star interior. And where the free protons are present, they also pair together and form a superconductor. Because the interaction here, is mediated by nuclear forces, the transition temperature is extremely high. So these are the highest TC superconductor and superfluids known in nature. Cooper pairs are formed due to strong interaction, and the TC works out to be about 10 to the power 8 to 10 to the power of 10 Kelvin. It beats any TC of superconductor which you know in nature, but on the Earth. And that's because there we are talking about Coulomb interaction, which are much weaker. than strong interaction. So this is one of the interesting properties of neutron star interior, and the neutron stars also rotate very fast with periods of the order of milliseconds to minutes, have strong magnetic fields, Tera-Gauss magnetic fields. And these cause this well-known phenomenon, which we call pulsars. A flash of radiation is seen every time a beam which is attached to the magnetic pole crosses our line of sight. Majority of these are visible at radio wavelengths, and these are extremely good clocks, because every rotation period we see a flash of light, and this is a very stable rotation, and you can see it for a long time. As you follow the rotation speed, you see that the star regularly spins down. It spins down because the radiation that it is producing is coming at the cost of rotational energy, so it spins down. But every once in a while, you see a glitch, so it suddenly spins up a bit. And that's because there is slight decoupling of the crustal moment of inertia with respect to the rest of the star. But what is interesting is that after the glitch, it takes a long time, months to years, for the neutron star to recover its spin down rate. And this long recovery time is attributed to the fact that the viscosity of the material which is recoupling is very, very low. And that is evidence of the superfluid that is predicted theoretically in the interior of the neutron star. So this is one of the evidence that the theoretical predictions are actually on the right track about the interior of the neutron star, at least in the range where the nature of matter is still well understood. The major uncertainty of state of matter is actually in the inner core, where at density less than the nuclear saturation density, equation of state is very well understood. But at higher densities, additional species may appear. These could be hyperons, heavy mesons, quark matter, condensates of different kinds, and so on. And many-body interactions play a critical role. Many-body interaction producing superfluidity and superconductivity I just mentioned, but many-body interactions also influence what kind of different particles will be generated at very high density. And this remains one of the major sources of uncertainty. So this is a representation of an equation from state where here is energy per particle, energy per nucleon in MeV, and its number density of particles. And this is the prediction from different many-body calculations of what is the energy per particle. As you can see, at lower densities, various calculations, they all agree. There is no ambiguity at all. But as you reach the nuclear density, there is already a significant disagreement between different calculations. The predictions are different from different calculations. So, and as you go to higher than nuclear density, of course, these become much larger. The uncertainty becomes much larger. So that creates an uncertainty in the equation of state. Also, there is some uncertainty about what species will actually appear. The possible species that may appear at high density could be hyperons, which are heavy baryons. Mesons like pions, kaons, and if they do appear, they are likely to form their own condensates. Quarks can be deconfined. You can get phase transition to deconfined quark matter with hybrid matter in between. There is a conjecture that at very high density, a mixture of up, down, and strange quark matter can form a ground state which is below that of nuclear matter. So if that is true, then if you reach such a high density and make a transition to this ground state, then matter coming in contact with it can get converted to it, and the whole star may convert to this state, and such stars would be called quark stars. They have also been theorized. It's not as though that they have been found, but they have been theorized. Quark stars are self-bound configurations. They are bound by their own forces. Gravity only adds to it. However, all of these effects, new hyperons, mesons, quarks, and so on, tends to soften the equation of state related to that of pure nuclear matter. Soften meaning that the pressure at a given density becomes lower, or rate of change of pressure as a function of density goes down. So now, what are the constraints that we have on equation of state already? From laboratory, we know we can measure various things. For example, nuclear binding energies, neutron skin thickness, dipole polarizability, giant dipole resonances. So these are, all these can be measured in nuclear physics experiments. And then on the equation of state, we can put some general constraints. For example, causality. If you produce a pressure density relation where the sound speed exceeds the speed of light, obviously that is not acceptable. There's also thermodynamic stability, which means that energy density has to be positive definite, and it should be monotonically increasing function of pressure. So these are general constraints which you can put in constructing an equation of state. And take account of laboratory constraints, take account of general constraints, and create an equation of state from your own extrapolation of knowledge of laboratory constraints on nuclear matter. However, you can also put constraints from astrophysics, and these are from observations of neutron stars. And it is likely that over time, the observations of neutron stars are going to provide the most precise constraints on the equation of state at the highest densities. So what do you do in incorporating these constraints? So for example, here are various different equations of state. Each line is an equation of state in a pressure density relation. Each line is an equation of state. So various different equations of states have been constructed. In blue, it shows what regions are actually allowed by laboratory constraints. So if we take that region, and out of that, we produce a prediction of what is the mass radius relation of such objects. Any such equation of state will produce a mass radius relation. And those equations of state, which are allowed by these laboratory constraints, give us a range of mass radius relations, which are shown in this colored region in this diagram. So we predict that masses and radii of neutron stars will fall in this region given the constraints on the equation of state from laboratory experiments. So therefore, if you're able to measure the mass and the radius of a neutron star, you should be able to pick out which one of these allowed equations of state are in fact true in nature. And that is actually the exercise in astrophysics. The first exercise, therefore, has to be to measure the masses of neutron stars. An isolated neutron star sitting by itself, it is very difficult for us to measure a mass of it. However, if the neutron star happens to be in a binary system, then the Kepler's laws, and particularly in relativistic binary systems, the post-Keplerian parameters allows us to uniquely measure the masses of the two neutron stars. And this has been done for various binary pulsars, several of them. And if we look at the mass estimates of neutron stars in various types of binary systems, you can see that there is a range of measured masses with different degrees of confidence. The best measured masses are those with double neutrons in double neutron star systems or neutron star white dwarf systems. And these are given with the smallest error bars over here. And among them, the highest mass measured is about 2 solar masses. Now this already is a constraint that rules out certain equations of state. Because here are different equations of state which they, in the mass radius relation, they predict. And each of these, as you can see, has a maximum mass limit. And if the maximum mass limit happens to fall below the highest measured mass that we have, then that equation of state is ruled out. So here we have indicated some measured masses, and you can see that some of the equations of state do not meet this within their maximum mass. So therefore, those equations of state will be ruled out. Those which cross it will, of course, survive. So how can we make a distinction between them? So we have to see whether we can find heavier masses and rule more of them out, or for any of them, if you are able to measure both the mass and the radius, then that would be fantastic. So there is an effort, ongoing effort, to try to measure mass and radii of neutron stars. One way that has been tried for a very long time is to have an accreting neutron star in a binary system, where a donor star supplies matter to the surface of the neutron star, the matter accumulates and gets very hot and undergoes a thermonuclear explosion at the surface. And when the thermonuclear explosion happens, when the luminosity reaches a certain value, material is lifted from the surface. And at that value, we can say that we have reached a limiting luminosity, which is called the Eddington luminosity, which just balances the gravitational force on the matter with the radiative force. And since the radiative force can be measured from luminosity, we can measure the gravitational force on the matter. So that gives us an estimate of the mass. And if I find the temperature of this surface at that time, then from the total luminosity, I can also measure the radius. So this is the basic idea, that you measure the temperature and the luminosity of the material at the time when the material is just lifting off the surface. And so then you equate 4 pi r square sigma t to the power of 4 to the luminosity, and measure the radiation pressure to the gravitational pressure on the matter. And through that, you get an estimate of both mass and radius. You can constrain both of them. However, there are many, many experimental uncertainties which has made it difficult for this relatively straightforward conceptual method to give very good constraints as of now. So here are some constraints from one object. So you can see that the mass radius boundaries are somewhat wide. Although it does produce some constraints for equation of state, it is still not good enough to single out equations of state by themselves. Another approach that is being tried now is to look at the surface of a hot neutron star with a hotspot which produces a pulse emission. And this hotspot, as it goes around us, the neutron star being a general relativistic object, the light from there undergoes light bending, it undergoes Doppler effect, it undergoes propagation delays. All that, if you put together, you find that you predict, depending on the mass and radius of the neutron star, a delay between the phase difference between the way the temperature or the color changes as a function of spin phase and the flux of the intensity changes as a function of spin phase. If you can measure these phase difference, you have a measurement of the compactness of the neutron star, mass and radius of the neutron star. And this is an attempt that is being made by this dedicated mission, which is called Neutron Star Internal Composition Explorer, NICER, which is a NASA mission about International Space Station, which is currently already operating for a few years, and some measurements are already available, and it is beginning to produce certain constraints. We will wait for some more time to get the full result of this mission. And another front that has opened up recently is from gravitational waves. And we know those LIGO detectors, there are 2 of them in the US, the third one is going to be built in India. And there is a Virgo detector in Germany, the Kagra in Japan. These are all being used to find gravitational radiation from merging neutron stars. And one interesting aspect of merging neutron stars, rather than merging black holes, is that when the neutron stars are about to merge, the objects get tidally deformed. And this degree of deformability depends on the equation of state. And the amount of deformation can cause a deviation in the gravitational wave waveform compared to, let us say, the merging of 2 point objects. And if this departure in the waveform can be measured, we can measure the deformability of the neutron star. And from the deformability, we can then get an idea of the equation of state. And here is prediction of as a function of m by r. Here is a measure of deformability. And these are for different equations of state. And from measurement, then one has to compare what one actually sees. There is only one object for which this has been possible so far, and that is GW 170817, where both electromagnetic and gravitational waves were observed. And in that object, we can see that there are constraints which can be produced, which begin to now rule out some of these equations of states which are very stiff, which survived the mass limit constraint. But through this measurement of gravitational waves, we can now begin to isolate some of these equations of states as more probable than others. And as more such events occur, more measurements occur, we will be able to see a better and better improvement of this method, as well as other methods also will improve with time. So therefore, from the astrophysical measurements like neutron star mass and radii, we will finally be able to get a constraint on what is really the equation of state of neutron stars. So therefore, what is really the density pressure relationship, and therefore what really is the nature of the strong force at very high density. That's all that I wanted to convey in this lecture. Thank you very much.
Please join with me for expressing our sincere thanks to Professor Dipankar Bhattacharya, distinguished professor from IUCAA Pune, for a very nice talk. Professor Bhattacharya delivered a very difficult concept in a very nice and lucid way. He is a great teacher. We are thankful for giving us your valuable time. So now it is open for discussion. Just one or two questions, because time is very short. You can give it in the chat box. So I want to ask one question, Professor Bhattacharya.
Yes.
The stable neutron star is because of the pressure degeneracy balanced by the gravitational interaction. Now, is it that it is only at the surface, or while going towards the center also, this is same, or there is a mismatch balance?
No, if an object is stable, it is balanced everywhere. Otherwise, if there is any unbalanced situation, that will cause, of course, dynamics. Matter will move. So when you say an object is in equilibrium, it is equilibrium everywhere. But degeneracy pressure is not the only pressure. Degeneracy pressure is only a part of the total pressure. If it was only degeneracy pressure, then there is a well-known limit called the Oppenheimer-Volkoff limit, which is the mass limit of a neutron star, which is 0.7 solar mass, which is even less than the white dwarf mass limit. So none of the neutron stars we see would exist if only neutron degeneracy was responsible for the balance. So nuclear forces are most important. And that is why the uncertainty, because degeneracy pressure, we don't have any uncertainty, because it's just a Fermi pressure, we can compute it exactly.
There is a question from Shyam Das.
Yes.
He is asking, can a compact object, not binary, create tidal deformation? If so, then how?
Any gravitating object can will produce a tidal field. So it will have a tidal effect on something else, right? A tidal effect is effect of one gravitating body on another. So for example, if a human approaches a neutron star, it will feel the tidal effect of the neutron star, right? That's what I said, that you will be pulled apart by a force which is 1 billion kilogram between your head and the foot. So any gravitating object will produce a tidal field. Just like Earth produces a tidal field on something that is on the surface, Moon produces a tidal field on Earth, and all that. So that is obvious. And so I'm not sure what other aspect was meant by this. But, tidal field is nothing but the gradient of the gravitational force. If the gravity place to another, then that's the tidal field. The rate of change of gravitational force is called tidal field.
There is a question from Sheshadri Mujumdar. What about the spin evolutions of pulsars on which it depends?
Okay, so let's take an isolated pulsar, which is not interacting with anything, not interacting with the binary system or binary companion. So the pulsar works because it has got strong magnetic field, and you have a rotating magnet, and this rotating magnet produces, through various mechanisms, produces radiation. And this radiation carries away energy. And why was this radiation created in the first place? It is because the star is rotating. So it carries away the rotational energy. And this rotational energy getting carried away causes the neutron star to slow down. So its total energy carried away by this radiative process, it could be all electromagnetic waves, it could be electron-positron pairs, but all of these things carry away energy from the magnetosphere. And that is what is responsible for it slowing down. So typically, it slows down like a spinning magnet. Sure. Sorry, I missed the first part of the question. Why what? Okay, so that is indeed what I tried to explain here. I don't know if you are still seeing my. Are you still seeing my slides?
Yes, yes.
Okay. Right. So neutron has a very small lifetime. It decays to proton and an electron if the electrons happen to be in a very low energy state. Now, if the electrons are in a very dense situation, then the energy per electron can rise to a value which is higher than the proton-neutron mass difference. So then, if neutron has to decay into a proton and an electron, it has to produce an electron which has to rise to such high energies, and such an energy budget is not available to the neutron. So neutron cannot decay. Instead, protons and electrons will combine to form neutrons, because that becomes energetically favorable. So at high densities, because the electrons have acquired a large Fermi energy, it is not possible for the neutron to decay to produce an electron of such high energy, because it doesn't have that much of energy available in the mass difference between neutron and proton. So neutrons remain stable.
So we are running out of time. Let us thank.
Sorry, I also started a little late, so unfortunately I couldn't contain.
We have any other question? Okay, one more question.
Not necessarily. I mean, it might be difficult because there will be complicated binary interactions. So some things can survive, some things may not survive. So it's not, there is no hard and fast rule that such a thing cannot occur. Only some configurations will be allowed, some will not be. In a triple system, typically the lightest member gets ejected after some time. But there are resonances where it can stay.
Yes, if there is no other question, let us thank Professor Dipankar Bhattacharya again for.
Thank you very much. Thank you for your invitation and thank you for this interaction.
Thank you. In future, you come to our university.
Yes, we don't know how
Well,
we'd love to. Yeah, thank you very much.
Thank you.
Yeah, bye.
Next talk is by Professor Gulab Divangan. Professor Gulab is working at IUCAA as a professor, and he is related to AstroSat program in addition to other like AGN and others. He visited our university many times. So because of this pandemic situation, it is not possible to invite the university campus. We are organizing online. So I hope that you will enjoy his talk. Professor Gulab Divangan, please start.
Thank you, Vikas. Thank you very much. Can you hear me clearly?
Yes.
Can you see my screen?
Yeah. Yes.
Okay. Okay, so I'll be talking on active galactic nuclei. This is the subject on which I have been working for a quite long time now. So as the name suggests, the active galactic nuclei are essentially nuclei of some galaxies which are active in some sense. Roughly 1 out of 100 galaxies is an active galactic nucleus. So given these numbers, how do we distinguish between a normal galaxy and an active galaxy? So of course we distinguish observationally. So if you happen to take a photograph using a telescope, let's say, if you are take a snapshot or very short exposure of a normal galaxy, then what you see initially, depending on the brightness of the galaxy, you may not see anything. But if you keep on increasing the exposure time, then you will gradually see diffuse emission. Of course, the central region will be slightly brighter, but usually you will see diffuse emission in case of normal galaxies. While in the case of active galaxies, if you take a snapshot, then what you see is a star-like nucleus. You will see a star-like object, and if you keep on increasing the exposure time, then of course the brightness of this nucleus will increase. In addition, you will start seeing diffuse emission from the host galaxy. So this very bright star-like nucleus is the signature of the presence of active nucleus in a galaxy. And this is not the only signature. There are a number of other observational signatures at different wavelengths. So by active galactic nuclei, we mean nuclei of galaxies that are active in some sense. That means they have an energy source other than the stars. So these objects are called AGN if the activity is substantial in some characteristically determined observationally. For example, you see in this image, this is the nucleus or the active galactic nucleus, and you see jets emanating from the nucleus. These jets emanating from the nucleus are shows the signature of the presence of active galactic nucleus. So there are other observational characteristics. For example, in the optical and ultraviolet, if you take the spectrum of an active galaxy, you will see emission lines. Some of them are very broad. The velocity width can be 5,000 kilometers or 10,000 kilometers per second. That means the line emitting material is moving with that kind of speed. How do we characterize the active galactic nuclei? So the active galactic nuclei can be radio loud as well as radio quiet, depending on the presence or absence of the jet. So here I will mainly talk about radio quiet active galactic nuclei, where either the jet is not observable or the jets are very extremely weak. So generally, observationally, we characterize regions by requiring that they have a large luminosity in the of the order of 10 to the power 42 to 10 to the power 48 ergs per second. And this is really a huge luminosity. You compare this luminosity with the luminosity of our sun, which has 10 to the power 33 ergs per second. So the AGNs have luminosity something like 10 to the power 9 times the luminosity of the sun, so to 10 to the power 15 times the luminosity of the sun. So this is a huge luminosity, and this huge luminosity is coming from a very, very compact region, as I showed earlier. So the nuclei of active galaxies are very bright. So these nuclei are essentially confined in very, very compact size of the less than about much less than 1 parsec. And these active galactic nuclei, broadband continuum emission, they emit in the radio, they emit in the infrared, they emit in the optical, ultraviolet X-rays, hard X-rays, gamma rays, all the way throughout the electromagnetic wave bands. A large fraction of this active galactic nuclei show strong emission lines in the optical and UV spectrum. Almost all active galactic nuclei emit in the X-ray band, particularly in the soft X-ray, hard X-ray band, and there are a small fraction of AGN which also emit very high energy radiation in the gamma ray band. In almost all wavelengths, these AGNs are strongly variable, but at shorter wavelengths, the AGNs are even stronger, even strongly variable compared to long wavelengths, for example. As I had mentioned, a small fraction of AGNs also show strong jets and lobes, and these are the radio loud AGNs, and the sizes of these jets and lobes can range from parsecs to kiloparsec and megaparsec scale as well. And these are really, really large sizes compared to the size of the host galaxy, which could be order of, let's say, 20 or 30 kiloparsec. So these are essentially the observational characteristics. Here I saw the images of active galaxies. For example, in the upper panel there is an image of NGC 1365 taken with HST and Chandra. In the inlet you see the X-ray image taken by Chandra, and here the star-like object in the X-rays is the active galactic nuclei, while in the optical image taken with HST, there is a huge dust cloud or obscuration of this light from the nucleus. So we do not see directly the nucleus because of this obscuration, but in X-rays we do observe this bright nucleus. Here is another example, this image in the far ultraviolet band taken by our own Astrophysics mission, Indian Astronomy mission. This is the image of the active galaxy NGC 4593. You clearly see very bright nucleus here, and the AGNs are very bright in the ultraviolet. Apart from that, you see the host galaxy signatures in the form of spiral galaxies. So what is the physical picture? What we understand about AGNs? We understand quite a bit, but not completely. Even today, there are lots of issues we do not understand, we are probing. But what we think from basic observations, for example, AGNs show very large luminosity, as I mentioned, 10 to the power 42 to 10 to the power 48 ergs per second. These large luminosities imply large mass at the center through the Eddington limit argument. The Eddington limit essentially says that any object cannot emit arbitrarily large luminosity because otherwise the radiation pressure will throw out the material. So the Eddington limit is essentially obtained by balancing the outward radiation pressure force and the inward gravitational pull. So, so using this, for example, here I have given the Eddington luminosity for an object with mass m black hole. So large luminosity of, let's say, something like 10 to the power 46 ergs per second or so. So that tells about the mass must be at least million solar mass confined into very, very compact region. So we are inferring just from this large luminosity. So a huge massive object is sitting at the center of the galaxy. And the size can be inferred from the variability. As I had mentioned, the AGNs, for example, in X-rays, ultraviolet, and gamma rays, etc., are highly variable on scales of few hours. And this tells us that the sizes must be very, very small. So what this means that the large luminosity tells us the huge mass, and huge mass is confined into a tiny, very, very small region. In physics, we do not know anything other than black holes having these characteristics. And now it is well established that the AGNs are essentially powered by accretion of matter by this supermassive black hole. The size scale for this supermassive black hole is of the order of Schwarzschild radius, typically you can say, and our luminosity, of course, is the order of initial luminosity. So these are some of the numbers one has to remember while studying active galactic nuclei. So after a lot of studies in different wavelengths, we have a rough picture of AGN central engine. So that the central engine is responsible for the production of a huge amount of luminosity. So what we think is that in the center of an active galaxy, there is a supermassive black hole with a mass maybe 10 million to billion solar mass or so, which may be rotating or may not be rotating. And this massive black hole accretes material from the surrounding and forms an accretion disk, because the material cannot directly disappear in the black hole, and because of the conservation of angular momentum, the accretion has to through an accretion disk. So this disk is thought to emit the ultraviolet, optical ultraviolet, and extreme ultraviolet continuum, which in AGNs we call is the big blue bump emission. And this big blue bump emission is thought to the direct signature of accretion flows around onto supermassive black holes. In addition, there are a number of other features. For example, surrounding this accretion disk, there are supposed to be cold, dusty torus, and this dusty torus can reprocess the emission from the accretion disk. So the accretion disk emission will get absorbed and re-emitted in the form of infrared emission. And what we find is an infrared pump at longer wavelength, below about 1 micron. Okay. If you go to higher energy side, a shorter wavelength side in the X-rays, for example, so what we think is that in the innermost regions, very close to black hole, there is something called hot corona, essentially made up of energetic electrons, and the temperature of this corona is about 100 keV or so. So in that case, what happens, there is interaction between the emission from the accretion disk and the energetic electrons in the hot corona, and that can give rise to a broadband X-ray power law continuum emission, which I will discuss next. Observationally, we find very different kind of AGNs. For example, some of the active galactic nuclei show broad emission lines in the permitted lines, for example, the Balmer H alpha, S beta lines, etc. While other AGNs have narrow emission lines. The narrow emission lines, widths can be only of the order of 500 kilometers per second or so, while the broad emission lines can have widths up to 10,000 kilometers per second or so. So how do we understand the different widths of the emission lines in AGN? So this is explained in the so-called the unification scheme. So as I was mentioning, the supermassive black holes are accreting, which forms an accretion disk, and this is surrounded by something called this cold torus. Now, if our line of sight is passing through this dusty torus, so what that means that the emission from the innermost regions, emission from the accretion disk and the hot corona are completely absorbed by this cold dust and torus. So you do not have the direct view of this accretion disk and the hot corona in the innermost regions. But what we have, the emission from regions which are quite further away from the black hole and maybe outside this dusty torus. So there are some kind of emission line clouds which are essentially photoionized by the radiation from the accretion disk. And as a result, these clouds, so-called the narrow line region clouds, give rise to these narrow emission lines, for example, in oxygen 3, S beta, etc. Because these clouds are quite far away, so therefore they are moving with much smaller velocities compared to the clouds which may be in the inner regions. So because of this narrow line region clouds, we get this optical spectrum with narrow emission lines. On the other hand, if your line of sight does not pass through this torus, but we are viewing through an angle where we have a direct view of this central region. In that case, we have the view of the accretion disk emission, the big blue bump, as well as there are other kinds of clouds very close to black holes. These clouds are called broad-line region clouds. Again, these broad-line region clouds are photoionized by the continuum emission from the accretion disk. And as a result, these broad-line region clouds, which are closer to the black hole, are actually moving with much higher speed compared to these narrow-line region clouds. And these clouds give rise to broad emission lines with widths of the order of 5,000 to 10,000 kilometers per second. So that's how, just based on the different viewing angle, we can explain the different types of emission line spectrum of AGNs. And the AGNs which emit these broad emission lines as well as narrow emission lines, they are called type 1 AGNs, while the ones which only emit the narrow emission lines are called type 2 AGNs. In the innermost regions, of course, we have the supermassive black hole and accretion disk, and the hot corona, which is giving rise to X-ray radiation. We are quite sure about these components, but exact geometry is not well known, and because we cannot really image, we do not have the instruments to resolve these regions in the UV or ultraviolet radiation. So, but what we think are the kind of configuration that can explain observations are given in the right-hand side. So, it is possible that the inner regions has a compact hot corona. So what will then happen? So this radiation from the disk, which is giving rise to the big blue bump, will interact with this hot corona and give rise to this radiation. Or it is possible that the hot corona is actually the base of a jet. And this, again, if it is the base of the jet, of course, it will be very compact. And the interaction between these optical photons from the disk and the hot electrons in the base of the jet will produce again the broadband X-ray Paula continuum. But we are not very much sure which of these geometries are slightly different kind of configurations actually within the AGNs. And it is also possible different AGNs may have different geometries in the innermost regions. But this is one of the subjects which people are working quite a lot. As far as the study of central engines of AGNs are concerned, the X-ray emission, X-ray radiation turns out to be the best probes, are the most important probes of the AGN central engines. Why is that so? Let me explain very briefly. So if you look at the variability, for example, in the optical ultraviolet, the variability time scale is in days, for example, 1 to 10 days. And if you use causality argument, this variability time corresponds to of a side scale which will be less than about 0.001 to 0.01 parsec. So what this means is that with the observations in the optical ultraviolet band, we are probing the regions of with sizes about 0.01 parsec or so. And this is the region where the broad emission lines, for example, arise. So we see these broad emission lines. While if you look at the time variability of X-ray radiation, the X-ray is very much faster on hours time scale, and this hour time scale variability translates to side scale of 10 to the power minus 5 parsec, much smaller compared to the side scale probe by optical ultraviolet radiation. And if you compare the side scale probe by X-rays with the Schwarzschild radius for different black holes, then you already find that this size scale, the Schwarzschild radius for let's say for about 10 to the power 8 solar mass or so is comparable or almost similar to the size scale probe by X-ray variability. So this is the reason why we think that the X-ray radiation is arising from very close to the supermassive black hole or in the immediate environments of supermassive black hole. And therefore, if you want to study or probe the immediate environment of supermassive black holes, X-rays are the best probes for this purpose. So how does, let's look at the X-ray emission characteristics of active galactic nuclei. So first of all, we observe X-rays, the individual photons in the X-ray band, and we work in the photon number flux rather than energy flux, because we are detecting individual photons. And if you plot this X-ray spectrum of AGNs, so it looks like what is shown in this figure. So this is a log-log plot. So a linear line in this plot is actually a power law spectrum. So now you will see roughly the AGN spectrum, Broadband X-ray spectrum of AGN is like a power law. But of course, there are departures. If you carefully see, below about 2 kV, the spectrum of this AGN PG1416 has an excess emission below 2 kV compared to this linear line in the log-log scale, or compared to a power law spectrum. And at the high energies, there is a deficit of emission above about 100 kV or so. So this power law does not extend to very high energies, but it cuts off at a few hundred kV. Okay. There are different kind of AGN, for example, NGC 4151. This one is an absorbed AGN. So what happens, there is an intervening medium which is absorbing X-rays at low energies below a few kV. You do not have strong X-ray emission. So this cutoff is not intrinsic, but due to absorption of X-rays to the intervening medium. Again, this region also shows a high energy cutoff at few hundred kV. So what is the physical process giving rise to this kind of a power law spectrum which dominates the broadband X-ray continuum? This process is thought to be the quantization in a hot corona. So in this, we have a model so-called the two-phase model. So what we have here, there is an accretion disk with a temperature of 10 to 20 electron volt, and there is a hot corona with a temperature of about 100 kV. So if you compare the temperatures of these two mediums, then accretion disk is like a cold disk, while the hot corona is obviously hot. So because the accretion disk is cold with a temperature of 10 to 20 eV and it is optically thick, it emits a spectrum, Blake body-like spectrum. Of course, the temperature varies from the innermost regions to outer regions. In the innermost regions, the temperature is highest, and the temperature quoted here is the temperature for the innermost region. So the innermost region emits extreme ultraviolet radiation, sometimes in the softest X-rays as well, while the outer regions are in the disk emit optical and near-infrared emission. So these photons, optical ultraviolet photons from the accretion disk, interact with the energetic electrons in the hot corona, and this interaction is through inverse Compton scattering. And the photons can undergo multiple inverse Compton scattering, and that process gives rise to this power law form of X-ray radiation. So how does it happen? So imagine you have the Blake body emission from the accretion disk, and given that the temperature of about 100 kV and optical depth of this corona is less than about 1, it turns out the corona is optically thin. In such a situation, a fraction tau, which is optical depth and less than 1, is inverse Compton scattered in one scattering state, let's say. And in the second scattering state, again, after the fraction of this Blake body component, which has been scattered in the first scattering state, again gets inverse Compton scattered, and this process continues until the energy of these photons, initially from the accretion disk, reaches to roughly the temperature of the hot corona, and then because there are no more energetic electrons, the corona is not dominated by energetic electrons with energies more than the temperature of this corona, then there is a usual cutoff. And that's why we see the cutoff in the observed X-ray spectrum. And this is the basic interpretation, or basic explanation for the origin of the broadband X-ray power law continuum emission from AGN through repeated inverse Compton scattering process. And we do see these cutoffs observationally. Now we have this new star mission, which has focusing hard X-ray optics, and this is a very sensitive instrument, and it has detected cutoff, this high energy cutoff at few tens of kV or even hundreds of kV from several AGNs. And by studying these data, people have now inferred that the temperature of this hot corona is something like 50 or 60 or 70 kV, depending on the different agents. So now the cutoff of high energy cutoff has been robustly measured in a number of agents, and this gives definitely a confidence that the process working in X-rays is the thermal componentization process. Do we really know this whether the seed photons for thermal componentization are actually arising from the accretion disk? There was not evidence, or there was no clear evidence for a long time. Recently, there is we worked on one of this AGM, and we saw that the UV radiation, UV continuum radiation from the accretion disk is really the seed photons for thermal componentization. And this was based on an observation with the ESA mission maximum Newton of an agent called Mercury 493, which has a black hole mass of about 10 to the power 6 solar mass. So what we did is that we studied the light curve in the UV and X-ray band, soft X-ray and hard X-ray band. Essentially, we looked into the UV intensity and X-ray intensity as a function of time, and then we studied the connection or the correlation between the UV radiation or the variations in the UV radiation and variation in the X-ray radiation. And what we found that if we do the cross correlation, then we see that the ultraviolet radiation is leading the X-ray radiation. So that is what you expect in the thermal componentization model, because the UV radiation is arising from the accretion disk at some radius, and this UV radiation has to travel to the corona and then get inverse components scattered many times. Then it gets converted into the X-ray photon. And in this process, obviously, the X-ray photons should lag behind the UV photons from the disk. And in this case, we found the soft X-rays to lead by about 5 kiloseconds, while hard X-rays to lead about 10 kiloseconds or so. So how we can quantitatively explain this the lead, the UV lead in the thermal componentization scenario. Let's see this. So if we have an accretion disk, of course, the temperature of this accretion disk varies as the radius power minus 3/4. So the innermost regions are have higher temperature and giving rise to extreme ultraviolet, while if you go to outer regions, then the temperature decreases. So therefore, this gives near ultraviolet, optical radiation, and near infrared radiation. And from the standard disk theory, you can actually find out a radiation at a given wavelength. For example, the UV radiation at 2000 angstrom, for example, where in the accretion disk or at what radius this radiation is dominantly arising. You can calculate that, and it turns out that the observed UV radiation with the maximum Newton is arising from something like that. That results in 7 kilosecond light travel time. Okay. And on the other hand, when the UV photon from the disk reaches to the hot corona, then it has to go multiple inverse component scattering in order to get converted into the X-ray photon. So let's say this requires n number of scattering. Then initial energy, let's say E0, which is the energy of the UV photon, let's say, and after n scattering, it will get converted into X-ray photon, and then we can find out what is the number of this scattering required, and for each scattering, what is the time scale TC required. So then you can calculate the componentization time scale in order to convert one UV photon to X-ray photons. So using thermal componentization theory, one can write down the various expressions and calculate the thermal componentization time scale is about 1 kilosecond in order to convert UV photons to X-ray, and total in this case becomes about 8 kiloseconds, which is comparable to the UV lead we see with the maximum Newton observation. So this is one observation which tells that the UV photons are really the seed photons for thermal componentization. Now, I had shown you a spectrum which looked like power law, dominated by power law. Of course, there are departures from the power law. And now with the detailed study of X-ray spectrum, this is a schematic representation of this broadband X-ray spectrum observed from AGM. So there are various components. So again, this plot is log scale, and this is E square NE, or you can say nu F nu plotted as a function of energy, or EFE plotted as a function of energy. So in this case, a constant line essentially tells us that the spectral index is -1, or photon index is -2. So because the spectrum is dominated by a constant Z, so here this constant Z means the X-ray spectrum is dominated by a power law continuum with a spectral index of -1. Okay. And if you look at the low energy side, there is an additional component, the soft X-ray excess component, and then there are lots of this absorption features, absorption lines, absorption edges, etc. And at around 6 kV, there is a very strong line, which is the iron K-alpha line. And then in the 20 to 40 kV range, there is a hump kind of emission compared to this constant component, and which we call the reflection hump. And I'll explain you how do these components actually arise. And of course, there is a high energy cutoff at a few hundred kV. So let's look at some of these components, how these components arise, and how these components actually help to understand the physics of AC central engines. So the spectrum here I am showing is based on 900 kilosecond, roughly 10 days of continuous observation with the Chandra X-ray Observatory. And this observation utilized the high resolution grating spectrometers, and this is the resultant grating spectrum. So you may think that at the low energy side there are lots of noise, but it is not really. All these features you see, these line-like features, are actually real features in the spectrum. They are not noise. And what this means, there are numerous absorption lines or absorption features in the X-ray spectrum, in the soft X-ray spectrum of active galactic nuclei. How does this arise? So this the simple situation it can arise is that the hot corona is giving rise to the power law continuum due to this inverse Compton scattering process. And if there is an intervening medium, then this power law continuum has to pass through this intervening medium. And this medium will have a number of elements in different ionization stages. So therefore, this medium will absorb and give rise to absorption lines in the spectrum. But why do we see so many absorption features? For example, if you saw the optical spectrum, there are a small number of emission lines, for example, while in X-ray band, there are so many numerous absorption features. Why is that? So in the X-ray band, for example, from 0.1 to 10 kV, the elements which come into picture are the elements which interact with X-rays are quite a large number, from carbon to oxygen. For example, if you consider the K-cell band, what do you mean by K-cell band? You consider iron atom. So the energy required to eject one of this K-cell electron, and when the L-cell electron falls to K-cell, that gives rise to iron K-alpha line at 6.4 kV. So this is for neutral iron. But if you take, let's say, highly ionized iron, helium-like iron or something like that, then or let's say hydrogen-like iron, then to eject that last electron in the highly ionized hydrogen-like iron, that takes about 9.1 kV. So for iron atom, we say that K-cell band is from 6.4 to 9.1 kV. And we are talking about, just for iron atom, from neutral iron to hydrogen-like iron. So there are a large number of ions. For example, neutral iron, singly ionized iron, doubly ionized iron, like when we have 25 electrons removed, which is hydrogen-like iron. And these so many ions have their own energy level diagram, and therefore transitions of their own. So iron atom itself can create huge number of transitions in the 0.1 to 10 kV X-ray band. And iron is just one atom. In addition, the K-cell bands of carbon, nitrogen, oxygen, neon, all the way to iron, all fall in this X-ray band and give rise to the spectral signatures in the X-ray band. In addition, the L-cell band for several other elements from silicon, sulfur, argon, calcium, iron also fall in the X-ray band, particularly the soft X-ray band. This L-cell band also give rise to large number of transitions in the X-ray band. In altogether, therefore, you see huge number of transitions or these absorption features in the X-ray spectrum. And obviously, using this X-ray, these absorption features, one can characterize the environment of region. What kind of elements are there? What are the evidences of those elements? What is the physical conditions? Whether they are moving, are they are in outflows or inflows? All these things can be characterized using this kind of absorption spectrum. The another component is this iron K alpha line at 6.4 kV. These are some of the example of observed iron K alpha line. This was this observation of external Newton observation of MCG 52316, which I performed during immediately after my PhD when I was a postdoc in the US. So what we detected a broad iron line in addition to a narrow iron line. The broad iron line, when you describe with the Gaussian and find the FWHM, a full width at half maximum of this broad line, that turns out to be about 50,000 kilometers per second. And obviously, this width is much larger compared to the width of the broad emission lines in the optical and ultraviolet, where we see typical widths of 5,000 to 10,000 kilometers. And this was 50,000 kilometers per second. So this immediately tells us that the line can has to come from innermost regions compared to the broad line. This is another observation of the same object with the same satellite, but for longer exposure time, and as well as with the Japanese Suzaku mission. And this again, this shows again a broad iron line. It is in a disk. Because there is some. Is there someone saying something?
Shonok, you switch off the microphone. Okay, now it is okay.
Okay, all right. So how do this broad emission lines or the emission spectrum arises in region? So this arises from so-called X-ray reflection. So what happens? We have this hot corona which is giving rise to the power law continuum. The power law continuum here is shown as a dashed line because this is again log scale. So the linear line is essentially a power. So when this power law continuum illuminates the accretion disk, then there's an interaction of this X-ray photons and the material in the accretion disk. The temperature is something like 1020 electron volt. So hydrogen may be ionized, but the heavier elements are not ionized. So there are free electrons as well as the atoms which are not ionized and they have bound electrons. So the free electrons will of course scatter the X-ray radiation due to the Thomson scattering, while the atoms will absorb X-ray radiation through photoelectric absorption. So what happens if there is a photoelectric absorption, then the K cell electron is ejected and there is a vacancy, and L cell electron jumps into this K cell, giving rise to K alpha photon, or this K alpha photon can knock out another L cell electron, giving rise to OZ electron. For heavier elements such as iron, the fluorescence yield is higher compared to the OZ effect. Therefore, you see very strong iron K alpha line because of this effect, as well as due to large cosmic abundance of iron. And that's how you see the strong iron K alpha line from the accretion disk. In addition, there will be weaker lines from other elements as well. So this is the spectrum. And then at higher energy, due to the constant recoil, the highest energy photons will lose their energy, and they will come to at lower energy, something like 2040 keV. And at the lowest energy, because of this photoelectric absorption, there will be again a deficit of emission compared to this power law. So this the combination of this effect due to constant recoil and photoelectric absorption at lower energies, that gives rise to a hump kind of emission in the 20 to 40 keV, which we call Compton reflection hump. So this is the spectrum in the red color shown here. Is the reflected spectrum as a result of the illumination of X-ray power law continuum from the hot corona onto the acquisition disk. So acquisition disk works like a mirror, and it gives rise to this reflected spectrum. And because these lines are coming from acquisition disk and from the innermost acquisition disk, and that these line emission can be modified by strong gravity in the following way. Let's imagine, in order to understand, let's imagine an acquisition disk and two rings in the acquisition disk, and this, let's imagine the emission from these two rings. According to, because the disk is rotating, if you just apply Newtonian physics, then you will see double horn-like profile because of this rotation. Because the speeds, the rotation speeds in the innermost regions can be very high in the acquisition disk, and you will need to account for the effect of special relativity. In that case, what happens with the beaming, special relativistic beaming effect, the line emission which is coming from the disk which is moving towards us becomes much stronger, while the line emission from the disk which is moving away from us becomes much weaker. So the line profile changes like this. And also because of this transverse Doppler shift, there is a red shift, the entire profile shifts towards lower energy. While you apply general relativity, because of the general relativistic effect at gravitational redshift, the lines are the line emission is even broadened. You will see extreme stronger red wing because there is a gravitational redshift in this line. And now, if you sum these profiles, sum these effects, and from a final line, you will see a broad, skewed relativistic iron line from an acquisition disk around a black hole. And this kind of the line profile was actually observed first time in 1995 with the Japanese satellite IUCAA, advanced satellite for cosmology and astrophysics. And the data can be well modeled by this broad, skewed relativistic iron line from an acquisition disk. And this is the first time when people started probing. There is proving strong gravity in the immediate vicinity of supermassive black hole, and since then the study of iron Kelp line and the reflection spectrum is being done very seriously to probe the innermost regions. Here, the example of how the relativistic blurring affects the entire reflection spectrum. In the black, what is shown is the spectrum for given the instrument resolution. So there is a slight width, but that's due to the instrument resolution in a way for typical instruments available. But when you blur the spectrum due to relativistic effects, then it changes into this red color spectrum. You see how the iron Kelp line becomes very broad, how the shape of this continuum changes, and in the soft X-ray band, you had earlier numerous discrete features which become much smoother due to this relativistic blurring. So therefore, by measuring the amount of blurring, you can prove the strong gravity in this. So that was the simulations, in fact. But we do observe spectrum which look very similar to what we expect. For example, this is the spectrum, broadband X-ray spectrum from for an object called AGN called Swift J2121.4. You see the new star spectrum and XMM new spectrum combination. Here you see the strong soft X-rays, which looks like the reflected and blurred emission in the soft X-ray band. Of course, there is a Kelp line, broad iron line, and then this reflection hump in the 20 to 40 keV. Then there is another spectrum marker 335 with very similar characteristics. So this kind of suggests, okay, now we are indeed observing relativistic effects near the black hole. This is another very interesting observation of Markarian 335. So you see here, these are the data points in the gray color with the white solid points. Then there is a model, blurred and unblurred model. You see how well the blurred relativistic model fits to the data, while in the blue color you see the unblurred model, and you see the difference in blurred and unblurred models and how this broad iron line comes into picture because of this relativistic blurring. And these are the kind of source or signature of relativistic effects in AGN. This is another observation of broad iron Kelp line from a well-known AGN energy 63015. Here you really see the broad iron line extending down to about 3 kV or so. There's such a line emission, such a broad line with a strong red wing requires emission below 6 times RG, which is the innermost stable circular orbit for Schwarzschild black hole. Of course, for rotating curved black hole, the innermost circular orbit can be smaller. For extreme the curve for a curved black hole with the extreme value of spin, the innermost radius can be just gravitational radius. And this observation of very strong relativistic iron line suggests that we are actually observing emission from below the innermost circular orbit for a Schwarzschild black hole. Therefore, in this particular case, the black hole must be a curved black hole. There are additional observations which essentially prove that there is relativistic effects. So in this case, this is an observation of 1s0707 by XMM Newton, and here is the spectrum, X-ray spectrum, which is essentially the ratio of this power law continuum and the observed data. So you see very strong iron L line near 1 kV and a very strong iron K line near 6.44 kV. So the emission below 1 kV is essentially dominated by this iron L line and therefore by reflection. While between 1 to 3 kV there is almost no reflection. So one can see there no reflection means it is the continuum, illuminating continuum. So then one can study what is the relationship between the continuum, illuminating continuum, and the reflected emission. So when people studied the cross spectrum, then what they found is this spectrum shown in the right hand side, okay, the figure showing. So this is the time lag as a function of temporal frequency. So what you see at low frequencies, you see positive lags, which are called the hard lags. So what happens in this case, the 1 to 3 kV band actually is lagging behind the soft band. Okay, but at higher frequencies, higher frequencies are slightly shorter time scales on the order of 1,000 seconds or so. If you are looking at the variability on these time scales, then there is a negative lag, or in this case, the soft band dominated with this iron L line is lagging behind the continuation. This is the signature for reverberation lag, where the continuum travels to the accretion disk, and therefore it lags behind. And therefore the reflected emission will lag behind the illuminating continuum. Okay, so illuminating continuum will reach first, and then the reflected continuum will reach to us. And this delay, what was found for this object, is about 30 seconds, and this tells us the distance of this hot corona. It must be very, very small from the black hole, and therefore the hot corona itself is very, very compact. The other component we have is the soft X-ray excess emission. This was discovered by my thesis supervisor KP Singh and Arnaud et al. Independently in 1985. For a long time, this origin of soft excess has remained a problem. We have working models now. One of course is this soft X-ray excess. That can be interpreted as a blurred reflection from accretion disk, and one can actually describe the data pretty well. But there are cases which are puzzling us. For example, this is one AGN called Arcalian 120. Here you do not see very strong or very broad iron line. What you see is more like a narrow iron line. So if you do not have a broad relativistic iron line, then you do not expect a strong blurred reflection in the soft band. But this AGN has a very strong soft X-ray excess emission is seen here. So this was puzzling. For such objects, another model was proposed. So in this model, so-called the intrinsic compliant disk model, suggests that the inner regions of the accretion disk is probably deviates from standard accretion disk age modeled by Sakurasani or relativistic version by Novicko and Thar. So what happens? Maybe the accretion disk develops a warm layer, or the disk itself becomes slightly warmer compared to what is expected for a standard disk. In such a case, this slightly warmer medium will inversely scatter the photons from the outer disk and give rise to the soft X-ray excess component which we observe. And this model also describes the data very well. This is one example. This is work from my student Lavani Malik. And this dotted line here is this intrinsic compliant disk emission, while the power law is the emission for thermal comparison from due to hot medium, and apart from that, there are reflection emission, distant as well as blurred reflection. But all this reflection emission cannot explain the soft excess. So you do need intrinsic compliant disk emission in such cases. In the last few minutes, I will just briefly tell you about the SOSET mission and how it is useful to study AGNs. SOSET is the Indian mission which was launched in September 28, 2015. It's going to complete 5 years very soon. It is a multi-wavelength satellite. It has optical ultraviolet, optical near ultraviolet, and far UV telescopes, as well as soft X-ray telescopes and hard X-ray telescope. So, and AGNs are obviously one of the multi-wavelength objects, and SOSET being a multi-wavelength satellite is good. It can probe both the accretion disk, giving rise to optical ultraviolet emission, as well as the hot corona and reflection emission in AGNs simultaneously. And this is very important because if you want to probe any connection between the disk and the hot corona, then you have to simultaneously observe and look at the relationship between the UV and the X-ray radiation, and that is what SOSET can actually do and study the interplay between the accretion disk and the hot corona. These are some of the examples here. So, for example, SOSET can provide us very broadband spectrum from the near UV to all the way to hard X-rays. This is one example of SOSET observation of PG0804. This one of this well-known AGN, and we can model this data with accretion disk as well as thermal componentization, and infer how much is the total energy output from this AGN, and it is emitting at roughly 10% of the Eddington limit. And there are a lot more other things can be done. For example, this is the SOSET observation of NGC 4593. Here you see the UVIT image in the far ultraviolet, while in the right panel I show the light curves in the X-ray band, the FUV band, and near UV band. Then, given these variations in the intensity in different bands, one can then study how the disk and corona are actually connected, how these two major components from AGN central engines are interacting and the radius causing variations in the radiation. So this, for example, in this case, when we do the cross correlation, it turns out that the UV radiation this time is actually lagging behind by about 50,000 kilosecond or so. So this means that the UV radiation must be the result of reprocessing of X-ray radiation in the accretion disk. So these are few examples what I showed, but there are many other problems which can be addressed with SOSET observations of AGN. And here I summarize. So measurement of hot corona temperature and UV lead will provide observational verification of thermal comparison models. Geometry remains uncertain. There are a number of AGNs UV emission is dominated by reprocessed X-ray emission. I just mentioned you one such examples. I just would like to say that SOSET is playing a significant role in understanding the disk corona connection in AGNs. SOSET is sensitive. SOSET sensitive is such that it is very good for nearby AGNs, but not very good for very distant AGNs because the sensitivity is not great. But as far as one wants to study nearby AGNs, and there are plenty of nearby bright AGNs which society is observing and producing interesting results. So here I will end my talk. Thank you very much for giving me this opportunity to talk to you. Thank you.
Please join with me for expressing our sincere thanks to Professor Gulab Divangan. Actually, astrophysics is a very exciting science now. So he has given a broad idea of what is going on in this area, from NASA data to Indian AstroSat data. So as time is very short, there will be one question I will ask to Professor Divangan from our faculty, Rajat De. What is the latest form of the galaxy luminosity function, including the lambda CDM cosmological framework, to fit hard or soft X-ray data from AGNs?
So first of all, one has to work on the X-ray luminosity function, not on the luminosity function of galaxies, because only AGN, when you are talking about the soft and hard X-ray emission, then one has to work on the X-ray luminosity function of AGN. And if you look at the X-ray luminosity function of AGN, okay, so not exactly luminosity function, but one has to look into the X-ray background. And then you resolve this X-ray background in terms of discrete sources, and almost the X-ray background is dominated by AGN. In that case, it turns out that the shape of the X-ray background fits in the hard X-ray band where the reflection emission dominates. So it is thought that a large number of absorbed AGNs are there, which essentially give rise to hard X-ray emission, and that can explain the X-ray background emission.
Okay, thank you. The participants will ask some question in your email.
Yeah, sure.
To give them.
Reply.
Okay. Thank you for joining us, giving your valuable time today.
Thank you. Thank you. Sorry for the time. I mean, I would have liked to interact with the participants, but because of the lack of time, everybody must be really hungry now.
Yes, thank you.
Thank you very much, Vikas.
Thank you. Now we move on to our last talk by Professor Anjan Sen, who is professor at Center for Theoretical Physics, Jamia Millia Islamia University, Central University, New Delhi. He did his master degree and PhD from Jadavpur University. Now he is a scientist at Center for Theoretical Physics, Jamia Millia Islamia University. And Anjan visited many places abroad, and he is a cosmologist, also involved with this large array telescope SKA, and we are eager to know from him about the present status of cosmology, or his or what he wants to going to speak. Please, Anjan.
Can everyone hear me?
Yes, yes.
Okay. So thank you, Professor Pal, for this invitation in this webinar. So let me start my. Can everyone see it? Can everyone see the screen? I mean, my slides?
It is visible.
It is visible, fine. Okay. So it's already quite late. I believe everybody is very hungry. So I'll quickly give you an idea about the dark side of the universe. Till now, all of the talks that have been given by different speakers, they are related to the lighter side of the universe, the bright side of the universe, where you have galaxies or you have stars, you have things like AGNs, planets. So now I'll talk about the darkness in the universe, fine? And the idea is that I want to sort of impress you that even if there are a lot of lights in the universe, in the form of stars, galaxies, and planets and everything. But ultimately, how old the universe is, how it is formed, and how it will be subsequently developed, or what is its future fate, everything is actually determined or sort of controlled mostly by the darkness in the universe. So that is the goal of this talk, just to impress you that this darkness of the universe is as much important as the lights in the universe. Okay. So just go to 450 BC. At that time, if you ask somebody at that time, what is the universe made of? Then the standard picture was that the universe was made of 4 things: water, fire, earth, and air. Fine. So this is the 4 things that people used to think that the universe was made of. In fact, interestingly, Aristotle also thought at that time that there is a 5th substance, and interestingly, he also named that 5th substance as quintessence. And he used to believe that that is the thing that is the heavens were made of. Fine. So Aristotle thought at that time that the heavens were made of quintessence. Fine. And we'll see that this quintessence is now one of the most important aspects of our cosmology. Now, if you come to around 1869, then if you ask somebody that what is the universe made of, then we know that Mendeleev gives us the periodic table of elements. And whatever we see in the universe that we are made of, you can find that everything is actually made of all these atoms that is there in the periodic table. And we call them usually the baryonic matter or the normal matter. Okay. But as human quest for means the universe is ongoing, so around 1970 and onwards, then as our understanding of particle physics and subatomic particles have more reach, then we have now a standard model of picture for particle physics. And we believe that all the things that are made of in the universe consist of leptons. There are 6 leptons: the electron, the muon, and the tau, and their corresponding neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. There are 6 quarks. So these are the leptons, and then there are hadrons like protons or neutrons, and they are made of 6 kind of quarks. Okay, and then we have 4 particles which are interacting, means which actually govern the interaction, different kind of interaction, whether it's electromagnetic interaction by photons, then weak interaction by W plus minus and G, and the strong interactions by gluons. Fine. And then there is another very important particle called the Higgs particle, which actually is important in the standard model picture of particle physics, because Higgs particle is the particle which actually gives the mass of any other elementary particle. So this is the standard model picture for the particle physics. So as we have from very early time, when you have only 4 quantities that we used to believe the universe is made of, then we have the periodic table, and now we have this standard model picture for the particle physics. But what do we expect when you observe the universe? So when you observe with a telescope of different kind, whether the space-based telescope or the ground-based telescope, so what do you observe? So this is a picture from the Hubble Deep Field observations. And as you can see, there are a lot of lights in these observations. These are different kind of galaxies, AGNs, neutron stars, all those things that we have in form of all these lights. But as you look at this picture very clearly, that with all these light, all these bright objects that we see in the sky, there are also a vastness of the dark side of the universe. There are a lot of darkness also. In between all these bright objects, there are a lot of darkness, right? So let's talk about these bright objects. So the observable universe has around 200 billion to 2 trillion galaxies, and they range from dwarf galaxies with few million stars to giant galaxies where you can have 100 trillion of stars. And typical mass of a galaxy is like Milky Way is around 10 to the power 12 of solar mass. Solar mass is around 10 to the power 30 kg. So as you can understand that if you look at this thing, the amount of the mass that is involved in all these bright objects in the universe. But as this cosmologist, way the universe, okay, they have a very, very surprising observation. What they observe is that all these stars and galaxies and everything, all these lights that you see, they only actually consist of 4% of whatever the universe is made of, okay? So these 4% is either in the form of heavy elements, neutrinos, stars, free hydrogen, helium, everything, fine? So this is the only 4%. So all these big, massive stars and galaxies and neutron stars, AGNs and everything, they only consist 4% of the observable universe. The rest of the 4 to 5%, the rest 94 to 95% of the universe are dark. And this darkness can be categorized in the two forms. One we call the dark matter, which is around 25% of the total universe, total observable universe, and around 70 to 71% we call the dark energy. In a dark, why we call dark? Because they don't emit any electromagnetic radiation, so they don't emit light, so we cannot see them by any telescope or anything. Why you call one as a matter and one as an energy? As you all know the special relativity. So if things are moving very slow in a sense, they are moving slower than, much slower than the velocity of light, then we know that they are very massive objects. Their rest energy is very, very high compared to their momentum or their kinetic energy. And we call them the dark matter. So these are the heaviest or heavier part of the darkness of the universe. On the other side, we have things which are very, very energetic. In that sense, they are very relativistic, okay? And they are very light in that sense. So we know that as we approach the speed of light, the things becomes much less massive. Like photon is a massless quantity, right? A massless object. So we have these in the darkness also. We have two kind of things. One is very high or non-relativistic, very high, massive or non-relativistic. We call them dark matter. They consist around 25%. And then on the other hand, we have roughly massless kind of thing, the component, which is very relativistic, and we call them dark energy. Energy because they are very, very relativistic, right? And they consist of around 70%. So this is the universe that we made of, that we can call. So this is, we call, say, periodic table for the cosmologists or astrophysicists. So the periodic table of cosmologists or astrophysicists is that there are 4% of bright objects or objects that emit light, and they are all that we have: stars, galaxies, all the people in the universe, all the mountains, Himalayas, and everything. And then there are around 90 or 95%, which is dark objects. In that dark objects, we have non-relativistic objects called dark matter, and you have relativistic things called the dark energy. So this 95% that we have in the universe is not present or cannot be explained, that is present in the periodic table that we showed or that we all know, or in the standard model of particle physics that we also know. Fine. So this is the biggest puzzle that we have currently, either in cosmology or in astrophysics or in particle physics also, because we don't know any fundamental particle or fundamental interactions that actually can explain these dark things in the universe. Fine. Okay. So, but as we know that these are dark, fine, they don't emit light. So how can we know that there is a dark matter or there is a dark energy? Because they don't emit light, I can't see them, fine. Just to impress you that obviously we can, even if they don't emit any light, but still we can feel their presence. This is a mission by NASA called the GRAIL mission. It's called the Gravity Recovery and Interior Laboratory Mission. It was done in 2011. So what they did, they put two satellites in the moon's orbit. So these two satellites called Ebb and Flow. So they are circling around the moon, and they can actually exchange signal in between them, and they can also exchange signal to the Earth base of the observatory. Right? Now, as they move around the Earth surface, the moon surface, if there is any sort of mass difference in the moon surface, if there is some mountain, if there is some crater or whatever, fine. Due to the gravity, their position can get shifted, and their relative position between them can get changed. And they are so accurate that they can measure distance up to, this change in distance up to micrometers, right? And by this way, what they did is that this is the moon surface, fine, that you can know through light. But this is the moon surface that they do with the change of gravity or the change of gravity due to defined mass distribution in the moon. So this Grail mission actually do a surface map of the moon by this experiment, fine. And as you can see, there's a color contour picture. So the darker color is basically massive. The lighter colors are basically less massive. And if you can zoom in, so this is a kind of a region. And then if you can see the actual surface of the moon, this is the actual surface of the moon. And you can see, okay, sorry. So you can see that this surface and this is actually sort of matching, fine. So wherever there is a less mass or there is a massive mass, means there is more mass, these can be actually fill, or they actually detected that thing or mapped that thing through the gravity, change of gravity, right? So just means why I am giving you this example is that even if the dark matter and dark energy, they don't emit any light, but as because they are present, okay, due to their presence, they have mass. And if anything has mass, they can have a gravity. So by gravity, means looking at their gravitational effect, we can detect the dark matter and the dark energy. Fine. So that is this thing. Now, so all those things actually has to be done under what we call the fundamental principle of cosmology. So what is that? The first, we know what is called the Copernican principle. It says that except the local inhomogeneity, like there are some of distribution, like we know that if you are sitting in a room, there's some people are sitting one side, some people are sitting another side, there's some vastness or the free space, like in the universe also, there are some collection of galaxies here, there are collection of stars there, there's a solar system over there, but in between there are a lot of free space, fine. So if we ignore these local inhomogeneities, the universe otherwise represents same aspects from every place in it, fine. So no matter where you are in the universe, it looks the same on cosmological scale, fine. Now, this is called, and this we call the universe is homogeneous and isotropic on cosmological scale. And when you talk about cosmological scale, we talk about 100 megaparsec or that kind of distance, with 1 megaparsec is around 10 to the power 16 meter. So what does it mean? It means that if you take a box of 100 megaparsec and 100 megaparsec and 100 megaparsec size, and you take this box and you take the box at the different part of the universe, and then you try to find out different statistical property of this box, okay? Then you will see that statistically, whatever the property of that box you take, they are same even you take this 100 megaparsec cube box at different place in the universe, fine? So, so if you coarse grain the system up to 100 megaparsec, the universe looks same at every point in the space, okay? And this is, we call the universe is homogeneous and isotropic on cosmological scale. This is one of the fundamental principles of cosmology on which we develop every other thing. So what actually does that is a kind of pictorial demonstration. Like as you can see in the middle, the thing is that it is homogeneous, but there is a direction, okay, preferred direction. So it is non-isotropic, but it is homogeneous. In another side, as you can see that it is non-anisotropic and also non-homogeneous. There is no preferred direction, but means there is preferred direction in different states, and also it is not homogeneous. Things, different places, there are more concentration and less concentration. Whereas in the left side, you see that this is isotropic, there is no preferred direction, things are completely random, and it is homogeneous in a sense that if you take any small region in any space, things looks more or less the same, okay? So this isotropic homogeneous, this is the kind of picture that we believe that our stars and galaxies and everything, every energy distribution in the universe is actually distributed around 100 megaparsec or so, that kind of a length scale, okay? What are the rules of the game? Universe must be described by 4-dimensional spacetime that we all know from the special relativity. We have 3 space dimension and 4th dimension is the time, okay? Then we believe that at the cosmological scale, gravity is the dominant force, okay? So there are forces like electromagnetic force weak and strong, but at the cosmological scale, gravity that governs the the universe. So all the things that is happening in the universe, the gravity is actually dominating. Okay, and then we think that the Einstein theory of gravity, which we call that the general relativity, okay, is the correct theory of gravity at that cosmological scale. Okay, and what this Einstein general relativity of gravity says? It says that the gravity is nothing but the curvature in the space-time. So the way the gravity actually behaves is nothing but that whenever there is a massive object, it actually curves the space-time around it. Fine. So it is, here is a picture that you have the sun and you have this moon. Okay. So as the sun is much more massive than the moon, so the space-time around the sun get curved. Okay. And now if the moon put moon in this space-time, then obviously the moon follows this curvature. And as because the moon follows this curvature, it will be, in a sense, you will feel that it is get attracted towards the sun. Fine. And one can actually show that from this curvature, if you calculate this curvature for any massive object, this force of attraction is, in a sense, it goes like 1 by r square, which is like the Newton's law. So what we can say that the gravity is nothing but the curvature of the space-time caused by the massive objects. Fine. This is the Einstein's general relativity. And as we have curved space-time, so then there can be different possible shapes in the universe. One shape is that we know, the spherical or closed geometry, that we always confined on a surface of a sphere, like we are on the surface of a sphere, like Earth is a spherical object, so we are on the surface of a sphere. Locally, we think that we are moving in a very flat space, but otherwise we are moving on the surface of a sphere. Fine. And how the geometry, the properties of the geometry on the surface of the sphere, that if you draw a triangle, the three angle of the triangle will not be 180 degree. So it will be greater than 180 degree. The circumference, if you draw any circle on this sphere, the circumference will be less than twice pi r. And if you draw two parallel lines, they will not be parallel always, they will meet. And we know that on the surface, all these parallel line ultimately meets at the pole. Fine. So these sometimes we define a quantity called k. We call them +1 for spherical or closed geometry. Then we have what is called a saddle geometry or hyperboloid, surface of a hyperboloid. Okay, and this is the reverse. That here, if you draw a triangle, the angle, sum of the angles are less than 180. The circumference is greater than twice pi r. And if you draw two parallel lines, they actually start diverging. Okay, so they always diverge eventually. And this k parameter, we sort of assign a -1 value for this hyperboloid or saddle-shaped geometry. And finally, we all know our very familiar flat or Euclidean geometry, where all these properties that we all know already. Right? So if you take all those things, like all this geometry, the fact that the gravity gives the curvature of the space-time and everything, then we come up with what is called the Einstein's equation. Okay, I am not going to any details; it is not important. But just to tell that there is a two-part in this equation. The part that is written r nu mu minus half r g nu mu into r, this is related to the curvature of the space-time. Okay, so this r nu mu is called the Riemann curvature. Okay, mu and nu runs from 0, 1 to 3. Okay, so this is called the curvature. This is related to the curvature part of the space-time, and this t nu mu in the right-hand side is related to whatever the matter distribution that we have. It can be sun, it can be earth, it can be galaxies, it can be dark matter, it can be dark energy or whatever. So whatever mass distribution or energy distribution that you have in the universe is in the t nu mu, and whatever this curvature of this t nu mu has created is there in r nu mu minus half r g nu mu into r. Now this lambda into g nu mu, this is another interesting term. I will come to this term in a minute. But what it actually says, that the matter tells the space how to curve, or rather space-time how to curve. This should not be space, this should be space-time. So the matter tells the space-time how to curve. And on the other hand, the space tells the matter how to move. So once you have a matter, it actually creates the space-time, a curved space-time. Okay, and now if you put any other matter in this curved space-time, this curvature will actually determine how that matter will move in this curvature in this curved space-time. Fine. So this is a two-way process. This is a reaction and back reaction kind of a process. Fine. Now, what is the problem of this thing? Now, once at that time when Einstein actually proposed this Einstein's general relativity, We don't have that much of a big telescope and all those things to look at our universe very, very precisely. And if you look at the sky in any time in the night, it looks that the suns are more or less motionless. All the stars are more or less motionless. They are not moving. Fine. So that was the Einstein idea. So he thought at that time the universe is static. Okay. But if you take this equation and you try to solve this equation, then one can show that, as you can understand, that the gravity is the attractive force. So if you have a mass distribution and energy distribution in the sky, so all these stars and galaxies and everything, so what will do? Now it will try to collapse, fine? Because due to the own gravity, everything try to collapse, fine? So that was the Einstein's problem, because Einstein thought that, okay, I think everything's static in the sky, but if I have all those this distribution of stars and galaxies and everything in the sky, then due to their gravity, they should always collapse, fine? Because they will come together to each other, fine? So he tried to, at that time, put something which can balance this collapse, so that I can get a kind of a static universe. So he wants to put some kind of repulsiveness in this Einstein's equation, so that the attractiveness that we have from the gravity, that is the usual attractive force, can be balanced by this repulsive force, so that the universe become a static universe. So that's why he put this lambda g nu term. In effect, if you put in Einstein's equation this lambda g nu term, this actually gives you the necessary repulsive gravity or repulsiveness in the universe that can balance the attractiveness of the universe, right? And that's why Einstein thought that he could manage to make the universe static. So this is called the famous cosmological constant term, as the Einstein introduced it in that time, in the very early time, more or less the same time when he wrote or write down this general theory of relativity. And the idea of Einstein to introduce this cosmological constant term was to make the universe static. But obviously, this was not, didn't last for long, because of these two great astronomers. One was Henrietta Swan Leavitt. So she was an incredible astronomer. She was working in the Harvard College of Observatory, and she was given the job of looking at different photographic players that have been taken from these different stars, fine? And what she observed is that there is a kind of a star that we call the Cepheid variable. It's a kind of a pulsating star. It pulsates both in its radius or diameter and its temperature, okay? And she observed that of these pulsating stars, there is a fantastic correlation between this pulsation period, okay, and the luminosity of the star. So that is the graph that I showed in this blue picture. And you can see that what she plotted is the period of pulsation in days for different pulsating stars and the luminosities. And as you can see, there is a nice correlation between the periods and the luminosity. So at any point, if I know the period of any Cepheid variables, okay, then I can straightforwardly get its luminosity, okay? So that is a fantastic thing that Leavitt actually discovered. And at the same time, there's another guy, Vesto Schleifer, okay? He worked all through in the Lowell Observatory in Arizona. Later on, he became the director of that also. What he observed also, the Doppler shift in the spectral line. So if you look, means he was observing like different spectral lines coming from different objects, astronomical objects. And what he saw is that basically the shift in the spectral lines, fine? Kind of a Doppler shift. Like if you look, let's say a carbon line or a hydrogen line or an iron line, I know that what is the rest frame wavelength of all these lines, fine? But as you look, those lines coming from all these astronomical objects, he observed that those lines are actually shifted. And we know that these kind of things means we know that this is what is called the Doppler shifting, because if something is moving away from you, then there is always a shift in the frequency, in a sense that the wavelength get to the larger values, fine? And we call them the red shifting, okay? So these are the two things that that was actually observed. One is this nice property of these Cepheid variables, where you can know just from the periods, you can know the luminosity of any object, and on the same time, by this Doppler shift, you can actually also calculate the velocity of objects, okay? And that was helped Hubble to discover, or the great discovery that the universe is expanding. And in that sense, the Einstein's biggest blunder of putting the lambda to make the universe a static universe, fine? So just using these two things, that the luminosity of objects from this period of the Cepheid variables, and also the velocity from the Doppler shift, what that the Schleifer has done. So what he actually calculated, because if you know that if I know the luminosity, so as you know that if I have a bulb in front of you, a 50-watt bulb, and I take the bulb at a twice of distance, the luminosity falls as 1 by r square. So, so if I know the actual luminosity of the Cepheid variables just from their periods, and then if I look at the Cepheid variables at different distances, fine, or I mean, I can look at the Cepheid variables, their luminosity, then I can know from their apparent luminosity that what is their distance. And at the same time, I can actually observe different spectrum of lines from those galaxies where the Cepheid variables actually stays, and I can actually calculate the velocities, okay? So what Hubble did, the same thing. So he actually plotted the velocities versus the distance, and what he get is a very, very nice linear relation between this velocity and the distance. And what we now call this as the Hubble law. So it says that the velocity between two galaxies, they are not zero. So they have a velocity, they are going away from each other. And this velocity is kind of linearly proportional to the distance between these galaxies, okay? And this proportionally constant, what we call the Hubble constant, fine? So this is the first time that the Hubble discovered around 1929 and 1930 that the universe is not static, but it is expanding, okay? So what does it mean? So like if you have the universe in homogeneous and isotropic in space, let's say, so if you have a box here, okay, size of a grid size, if you have a grid, and as you take the grid, it is always same, fine? So if you have any point in the grid, it looks, and you look around, you will see that everything is the same because this is homogeneous isotropic. Any point in the grid is equivalent to any other point, because if you sit at any point and look around you, if it is an infinite grid, if you look around you, you will find that you are looking the same thing, fine? Now, if you say that the universe is homogeneous and isotropic, not only in space, but also space and time, then what it means that with time also, if I take one grid, snapshot of grid in one time, another snapshot in grid another time, and another time, and another time, this will be also same with the time also, fine? So the things are not only homogeneous and isotropic in space, things are also homogeneous in time in a sense that with time, the grid doesn't change. So the grid distance between, so if I say that galaxies are sitting at each grid point, then it seems that the distance between galaxies are constant and they are not changing in time and they are homogeneous and isotropic, fine? But what happens that if the universe is expanding? So the universe is expanding is nothing but that as the time goes, the universe expands. But remember, my homogeneity and isotropy of space remains intact. That means what is happening is nothing but that the grid that you take at one time, with the time, just the grid is actually getting bigger and bigger and bigger. So the grid size is what is actually getting increased. Everything is remain the same, just the grid size is getting increased, fine? So even if now at any point, if you sit at one point and another point, you looks around, things are homogeneous and isotropic. Only thing it happens is that the distance between these two galaxies, which was there at some time t1, then at time t2, which is greater than t1, the distance between these two galaxies have increased, fine? So this is the coordinate system that we actually assume in when you do the expanding universe. We call this the co-moving coordinate system. And here, this grid size, in each grid size that we have, which is same in every direction, fine? The grid size are same in every direction. So this I draw in a 2-dimension, but in a 3-dimension, it is the same. And we call this grid size is something called scale factor. It is 80. So at any point, if I know distance between 2 points, okay, which is the grid size, okay, and then if I know the scale factor, then I just multiply by the scale factor between this in the earlier thing, and I get the new grid size, fine? So that is the way we write down the coordinate system. So this is a non-expanding flat Minkowski spacetime. So this we all know that it's a Minkowski spacetime written in a spherical coordinate system, spherical polar coordinate. The spacetime is written at spherical polar coordinate. Now this is a flat thing. What happens that if I have a non-expanding Minkowski space, but it is not flat, okay? So then the things that comes at that this dr part becomes 1 minus kr square, where this k can be 0, which is get the flat space, k can be +1 or k can be -1. So this is a non-expanding Minkowski space with spatial curvature, fine. But still, this actually is always a homogeneous, the space part is always homogeneous and isotropic, okay. Now, if we put an expansion, like previously that I depicted, how the way the grid size is increasing, so what happens is just the space part, the different distance between 2 points in the space is actually increasing. So what we do is just overall multiply a scale factor in the distance between 2 points in the space, because this term in the bracket is the distance between two space-time point at any instant of time. And then I multiply this by a scale factor so that this distance is actually, and this scale factor is not a function of r, theta or phi. So this scale factor is same in any direction or at any space, fine. So this is a metric that we take, which with a special curvature, and is a homogeneous and isotropic metric for a expanding space or expanding universe, fine. Now, if I use this metric and use the Einstein's equation, okay, what we get is that we can have this scale factor that we have over here. The scale factor that we have over here, which actually is the measure of this, how the different points, the distance between 2 points are getting increased by time, fine. So if I solve this A using the Einstein's equation, then there can be 3 solutions of this A. One is for k equal to 1, which is for spherical geometry. The A goes to a maximum and then a recollapse. So the universe starts with a point which we call the Big Bang. It goes to a maximum size, and then it again recollapse and go to another, again A equal to 0, we call it a big crunch, fine. So universe has a finite size over here, fine. If k equal to -1, then the universe actually expands, okay, and it means just expands forever with increasing values, fine. And if universe is k equal to 0, means flat, so universe expands, but ultimately it go to 0, the expansion goes to 0 at the infinity. So for k equal to -1, the expansion never, means the scale factor always goes, so the expansion never goes to 0. For k equal to 0, the expansion actually grows, but it goes to 0 at infinity, fine. So these are the 3 things that we can have when we solve this Einstein's equation without the cosmological constant, fine. If we add the cosmological constant, what happens that the universe actually expands initially, but at a slower rate, as you can see just from the curvature of this line or the slope of this line, the expansion is actually decreasing, fine. But as we approach the present day line, which is the red line, this expansion start increasing, and then it start increasing in an exponential way. So that is what is called the acceleration. So initially all these lines, you have the expansion which is actually decelerating. The A double dot is less than 0, fine. But only for the brown curves around the present time, the A double dot starts getting positive. So the universe started getting an accelerated expansion. Okay, so this is the peculiar thing that we have. Okay. Also, as we said, that we also described previously that what Schleifer described, what is called the redshifting of things, so that as the things goes away from us, if they are emitting some light, this light gets actually redshifting. And the amount of redshifting that we call this Z, this is related, one can show that this is related to the size of the universe, with the relative size of the universe when it was emitted and when it was received. We all receive the light today, fine, in our lifetime. So the TR is received is the present size of the universe, and A at TE is when the light was emitted. So the redshift from any object is proportional to, or it's related to, that what is the size of the universe today divided by what is the size of the universe when it was emitted. And as you can see that today the size is always greater than what is the size of the universe in the past, because the universe is expanding. So the redshift from any early objects is always greater than 0, fine. Okay, so this is also a way we can actually time stamping in the universe. Instead of by going time, we can also go by redshifting, so that higher redshift means more early objects, lower redshifting means more newer objects or more current objects. Okay. So what makes up the universe? As I said, there are stars and gases which are slow moving, okay, compared to the speed of light. So most of the energy is rest energy in E equal to mc square, okay, and we call them matter, fine. And as you know that if you're in a box, if the number density is nm, So the rho energy density in the box is Nm into mc square. That is the energy density. And as the universe expanding, and the expansion is going isotropically in all the directions, so the volume actually goes like 1 by a cube if A is the size of one side of the box. So the rho or the matter, whatever you have, this non-relativistic component, they dilute as the volume. So 1 by a cube, fine. So all the matter, whatever you have in the universe, non-relativistic matter, like stars and gases and everything, they actually dilute as the universe expands as 1 by a cube, where A is the size of the universe. Then we have radiation, that we can have a lot of radiation. We have a lot of lights in the universe, fine. We have lights coming from different stars and galaxies. We have lights there from the CMB photon, the cosmic microwave background photon. We can have radiation like massless neutrinos that can also contribute to the radiation. So these are relativistic objects, fine. So they also, like the matter, they also they dilute the number density as 1 by a cube. But on the same time, these are relativistic objects, so they have associated frequency or wavelength to it. And we already saw that as the universe expands, the wavelength gets redshifted. And the redshift, as I just showed you, the redshift is proportional to the 1 by a, the distance of the size of the universe, fine? So there is an extra energy loss of these objects, of these relativistic objects, due to the redshifting or due to the expansion of the universe. Because these are relativistic objects, I can associate their energy is h nu, and nu is related to the lambda, 1 by lambda. And as the redshift it goes, the lambda goes, so the energy also dilutes. So there's an extra 1 by a factor. So overall, all these things actually dilutes as 1 by a4. So it dilutes faster than the matter, fine? So we have the radiation in the universe, we have baryonic matter in the universe. What can we have else, and what evidence we have? So that was the first evidence that we have from the dark matter, okay, that we observed from this rotation curve. So if you can do the simple Kepler problem, so if you have a galaxies with a sum and you are observing objects which is around the galaxies which are rotating around, then we can have the mv square by r and gmm by r square thing. And from here we know that the velocity falls like 1 by square root of r, fine, the simple calculation. But what is, so that is the pink line, fine. But what is observed is that this flat plateau line where the velocity is a constant, that means the mass is actually proportional to r. So as we go out these galaxies, it seems that we are more mass, but that mass is not visible because we don't see that mass. But just looking that this rotation curve have a flat kind of a behavior, it actually predicts that there can be missing mass outside the galaxies or around the galaxies that we cannot see, fine. So this is what observed. So this is the M33 rotation curve. The Zwicky in 1934, he did this observation, fine. And as you can see that compared to, so this is the M33 galaxy, so compared to this falling line that we observe from standard Keplerian flow, there is a more or less kind of a flattened thing that we can observe for this rotation velocity. And from here, the Zwicky first sort of thought that there is a, and then Vera-Rubin, they have this thing that there may be an invisible matter in the universe. Whether there is an invisible matter, that I already told you in the very early time from the Grail, that even if there is a matter that is not there, but if that is present there, due to their mass, there is a gravity. So if there is a gravity, I can detect them by this gravity. One of this way of detecting through gravity things which is invisible is called the gravitational lensing. So it is just like that if you have an object, okay, which is a very massive, and there is another object behind it, like a quasar. Let's say there is a galaxy over here, which is very massive, and there is a quasar which is behind the galaxy, and the light is coming from the quasar. Then Einstein's general relativity tells that due to the curvature of the space-time around a very massive object, the light gets bent. So there is a gravitational bending of light, okay? Light, in standard case, the light gets bent when it goes from one material to another material. The speed of light gets changed, so it gets bent. So that's why we get the lensing effect, fine, that we know of. So here, light can bend just due to the gravity, okay? Just due to the gravity, the light can bend. And that is one of the prediction of the Einstein general relativity, and it was ultimately verified by Eddington, okay? So this, due to the bending of light, I can see these multiple objects of the quasar, fine? And these are called the strong lensing. So this is the one picture of strong lensing, as you can see. So this is, I am drawing the picture in 2 dimensions, but if you can look at the sky, there is a 3-dimensional way. So there can be some sort of an arc that you can see in this for these images, and these are called the strong lensing. So the looking at the strong lensing and looking at their arc and their size of the arc and the radius of the arc, one can actually get to know what is the mass. One can actually map what is the mass in this lensing galaxy. And as you look at the galaxy, I can detect the mass from there, whatever the light that is coming. And if I see that whatever the mass I detect from the light in this galaxy and whatever the mass I detect through the lensing, if there is a mismatch, means there are the more mass in the galaxy that is predicted by this lensing phenomena, then I know that there is some sort of an invisible of dark mass that is there in the galaxies, which is called the dark matter halo, that we cannot see through this normally with the light that is emitting from the. So this is another way one can detect the dark matter. Fine. This is, as I said, that this lensing can be, if you can have a wine glass, if you put that on top of a candle, you can see this lensing effect. Fine. You can see all this arc that is forming. And this is basically not due to gravity. This is just basically fact that the light goes from different medium, from one medium to another medium. Fine. But means amazingly, the same sort of things happening over here, the lensing effect, but this is just due to gravity. It's not a electromagnetic thing phenomena. It is just due to the gravity or the effect of gravity on the propagation of the light or the photon. Fine. There can be also what is called the weak gravitational lensing. So if there is not a very massive object, but let's say star forming or a galaxy, the star forming objects where there is some sort of a dark matter is present, it is not as massive as a galaxy or a cluster of galaxy, but still if it is present, and then if you look at in its background a portion of different galaxies, okay, then if this is the normal look, the way the galaxies look, then due to this dark matter, there are what is called the weak gravitational lensing, that we also know that in standard optics also in the lens, things can get distorted, fine. So that kind of distortion also can happen. So this is the original kind of it's a simulation picture. So this is a sort of what you can have the actual galaxies, but due to lensing, they can get distorted. And if you can measure this distortion, you can actually get to know the actual mass of that intervening objects. And from there, you can infer that there can be a dark matter. And that is what has been done by this Chandra telescope, the X-ray telescope, which is called the bullet cluster. Here, the two clusters actually collide each other, fine. And if there is a dark matter, they are non-interacting, they go past to each other. Now, you can see that just as the clusters collide, they emit lots of, they are in the cluster, there are a lot of gases and all those things, high energy particles. So when they collide, they emit a lot of X-rays. So these pink lights are basically whatever the X-rays that has been emitted by this cluster. And what is the blue light or the blue mapping is that as we see these objects, so it is a two galaxies, so they are colliding. So because they have a lot of dark matter, so if now you look in its background, some other galaxies, so the galaxies can get, all those background galaxies can have weakly lensed, okay? So I can measure the weak lensing, and then I can get to know that what is the mass distribution of these two galaxies. And then I can get this extra mass distribution that I don't see in the visible region. And this extra mass distribution that I have, that is kind of pictured here by blue. It's not that it has been emitting blue light, it's not. It is just the dark matter map of that has been done through the weak lensing. So this is one sort of a way that you can actually directly see that there's some dark matter in these two galaxies, okay? So that all these things actually give the presence of the dark matter. This establishes the presence of the dark matter, fine? So we have the radiation, we have the baryonic matter, we have the dark matter, and then what else we can have? And that actually gives you the stranger than fiction, the accelerated expansion, and the need of dark energy. So as I said you earlier that any light bulb can be, if you know their wattage, I can use it as a standard candle because the luminosity that we have and the flux that is emitted, that actually, so if we have a brightness, a 5 watt or 10 watt bulb, and then I put it at a different distance, the brightness of the bulb or the apparent luminosity of the bulb actually falls like 1 by R, 1 by D square or 1 by R square. So if I know the actual luminosity and if I know the apparent luminosity, then I can get to know the distance of these two objects, fine? So that has been done with a kind of objects in the universe called the type 1a supernova. And because these are considered to be a standard candle, we think that we know their actual brightness. And they are light, they are like a light bulb of 148 watts, fine? Just comparison to sun, the sun has a wattage of 10 to the power 26 watt. So these are, means 10 to the power 22 times more bright than the sun. Fine. So this is a hugely bright object. So what are these? So these are, I think, already has been discussed in previous talks, that we can have these objects like the white dwarfs. Okay, so they accrete mass from the nearby things, and then they reach their Chandrasekhar limit, and then they blow up. And this phenomena is all the type 1a supernova. I'm not going into details in that. But these were first proposed by Bade and Zwicky in 1930. They are extremely bright objects to be seen in the cosmological distances. And this is some sort of a light curve that you can see. So as you can see that it goes from 0 to the maximum brightness around 2 weeks, and then it takes around several months to drop below. Fine. And as we go to the maximum object, mean the maximum height, I can get to know its luminosity. Fine, the apparent luminosity. I know it's exactly what is luminosity. So from there, I can get to know its distance. I can see different colors that is coming from it at the peak brightness. Fine. And if that color I know, then I know its observed wavelength. I know its rest frame wavelength. And from there, I can calculate the red shifting or the Doppler shifting. And then I can calculate the velocity. So this is exactly what the Hubble did with Cepheid variables to get the Hubble's law. But this we do for supernova type 1a supernova, which are much further objects, more further objects. Fine, Cepheids are very nearby objects. So as I said, these are very bright. These objects are very bright. Okay, and they are very uniform. If you see the supernova in one galaxy than in another galaxy, faraway galaxy, their spectroscopic characteristics are more or less the same. Fine. So by doing this, by observing this, calculating their distance through their luminosity, and calculating their velocity or the redshift through their defined spectral lines, one can draw these graphs. Fine. So these are roughly around 700 to 800 supernovas observation till date. Fine. And this is the curve that we can see. Fine. Now, what is this curve? Means what is the curve that it represents? Interestingly, this curve represents that universe not only have some bright, like the light objects like stars and galaxies, which is around 4%. It has a dark matter, which is around 25%. But more importantly, it has a dark energy, which is around 70%. Now, what is this dark energy? That I will come to later. But first things, it is the first time through the supernova observation, people established that the presence of dark energy in the universe, and we'll see that this dark energy is extremely strange object that we never think that we have in our universe, right? So what it actually says, again, this is the y-axis, we have the a dot, which is the velocity, and the x-axis, we have the a. So this is the velocity versus distance. A is, as you know, that the distance between the two galaxies is the size of those block that I draw. Okay, and as you can see, as you go from past, so the A is small, means in the past A is larger around 1, for it is normalized that at present A is 1. Fine. So as you can see that the A dot, it actually decreasing with time. So A increasing means we are going from early time to late time. So as you can see, the data, the blue point, the red, black points are the data. So the data says that it actually decreasing. At some point, the data also says that these points are increasing. That means A dot is increasing. A dot is initially decreasing and A dot is increasing. A dot is increasing means that A double dot is positive, that the universe has an expansion which is accelerating. Fine. And there are different lines have been drawn. As you can see, the lines that is close to this, closely matches to these points is basically a point where the dark energy, the matter is around 30%, and there is a dark energy which is around 70%. Fine. And so this was that thing that I initially told you, that this pie diagram is actually coming from this picture. Fine. And this pie diagram shows that there is a 70% of dark energy. And this actually these three people, Paul Mutter, Brian Smith, and Adam Rees, they got the Nobel Prize for this fantastic discovery of 2011 that the universe has a accelerating expansion. So they have this observation in 1999, and for that they got the Nobel Prize in 2011. Okay. Now, what is this acceleration? Fine. What is so special about the universe expansion is accelerating? Fine. And if you look at this Newton's gravity, So the r double dot, so which is the acceleration, is always equal to 4 pi g rho, which is the energy density. But importantly, there is a minus sign, and the minus sign says that the force is always attractive. So if any point, if you have a gravity and you put any point in the gravity, so the point will be always attracted towards the source of this gravity. Fine. This minus sign actually shows that it is always attracted towards the source. Fine. It is not going away. Fine. So this minus sign is important, and it actually shows that the gravity is attractive. Now, how this equation, when I, instead of Newton gravity, I go to Einstein's general relativity, how those equation changes, okay? The equation changes in a sense that now instead of rho, you have a term called P, fine? What is the P? P is the pressure. So if you have, so let's say that if you have any energy distribution, it has energy density, okay? Rho is the rest energy density, and we know that in Newton law, only the rest energy density that matters, fine? But as you go to general relativity, any kind of energy that matters, whether it's a rest energy density or whether it's a kinetic energy or momentum, fine. So what is the pressure of any gas or any fluid? The pressure actually comes from the random motion of this particle, and which is the random kinetic energy of the particle, fine. So this pressure, so as because we are going to general relativity and any kind of energy gravitates, so not only the rest energy gravitates, the momentum, which is actually coming from the kinetic energy, this also gives a gravitating effect, and it also gravitates, fine. So in the effective mass, in standard Newton gravity, you have effective mass which just comes from the rest mass. But in the general relativity, not only the rest mass, but there is the effect coming also from the motion of this fluid or the random motion of this fluid or the kinetic energy of this fluid. And as I said, the universe isotropically is isotropic. So in the three defined direction, the kinetic energy is the same. So the three defined direction, the pressure are the same. So these three component of the pressure gives you a 3p contribution to the total energy density. So now the acceleration is now modified from rho to rho plus 3p. Now, as I said, the universe is accelerating. That means it's not decelerating. Fine, the universe is accelerating. If there is a minus sign, then r double dot means this is a decelerating. The acceleration is negative. Fine, the expansion is decelerating. But as we observe, the expansion is accelerating. So the r double dot has to be positive. So if it has to be positive, there is a minus sign. Then rho plus 3p has to be negative so that the r double dot can be positive. So to get an expanding universe which is accelerating, the rho plus 3p has to be negative. That means this term becomes positive, this minus becomes positive. That means the universe, the gravity has to be repulsive. Okay, so that we can also understand that if we have a particle which is moving with a velocity, then you put it under a attractive gravity. So if the attractive gravity will actually try to, so that let's say the universe is expanding, but due to the attraction of the gravity, the expansion will get slower and slower and slower. Fine. So this is, we can understand that if you give a ball of mass, an expansion which is going out, but due to the ball of mass has an attractive force, so this expansion will, due to the attractive force, will get slower and slower and slower. So that is we have due to the attraction. So the expansion gets deceleration. Fine. But now what we actually observe that the expansion is accelerating. So that means that whatever the attractive nature of the gravity, this has to be overcome by the repulsive nature so that the expansion is actually accelerating. And that we observe from here, that from the simple equation, the gravity has to be repulsive. Now, what this repulsive nature come? So if I have this P by rho, which is sometimes called the equation of status for any fluid. So a simplest model is that this P by rho is -1. So P equal to minus rho. So the only thing that we have from here, that rho is the rest energy density. So it's the mass kind of, is always positive. So the pressure has to be negative. So we should have something in the universe which gives rise to the repulsive nature of the gravity, and that thing should have a negative pressure. This is completely counterintuitive what we have from a positive pressure. Okay. So the dark energy which is giving you this accelerated expansion should have a negative pressure. Okay. If the pressure first has to be non-zero, like matter. In matter, I can ignore the pressure because it is non-relativistic. So I can ignore the pressure term in terms of the rest energy density. But for dark energy, I cannot ignore it. Not only that, the pressure has to be negative, fine, which is the very, very, very funny thing, fine. Just to show you that how as a gravitational potential, how you work. Let's say that we have a sheet, a rubber sheet. I put a ball, which is the attractive gravity. then I know that the ball will give you a deep potential wave. Fine. That gives you the attractive nature of the gravity. Fine. If it is a relativistic kind of thing, which has a much more energy, so the deep in the potential will be much bigger. If it is a non-relativistic, so the deep in that potential will be smaller. Fine. But the attractive gravity will always give you a potential wave. Fine. On the other hand, let's say I have a rubber sheet and I put there a chunk of dark energy. And dark energy has a repulsive gravity. What it will do? It will instead, it just deepen the rubber sheet. The rubber sheet will actually go up. So instead of a repulsive, attractive potential well, it will have a potential barrier. Fine. And that will actually repel. So this is a very, very funny property of dark energy, that instead of a attractive gravitational potential well, it will give you a repulsive gravitational potential barrier. Right? So that is one of the typical property of this dark energy. Now, what is this dark energy can be? The popular candidate is what Einstein's actually, remember the Einstein put the gravitational cosmological constant just to put a repulsive gravity. Fine. He tried to make it static, but ultimately we know that the universe is not static. But we already know from Einstein's introduction at that time that the cosmological constant is actually gives you a repulsive force. Fine. So these also now we can use to actually model the dark energy. Okay. And as you know that we wrote previously that it is lambda GIK, or if you write down mixed terms, so lambda del IK, and it gives you a, if you can do the calculation, it gives you a pressure which is just minus of rho. So the equation of state is minus 1. So this is the equation of state, the cosmology. What is the problem with that? You can do it very straightforwardly. It can solve all the problems. Fine. The problem is that we can calculate how much, because we know that how much the universe is accelerating. So we can actually calculate what would be the value of the cosmological constant to give you the present acceleration. Fine. So we can calculate observationally. Also, we can calculate cosmological constant from particle physics, from theory. So if you have a good particle physics theory, then we can actually calculate the cosmological constant, because this cosmological constant actually gives the vacuum energy or the zeroth order energy of a corresponding quantum field theory. We know that in quantum field theory, the ground state energy is not zero, or in quantum mechanics, the ground state energy is not zero. It always has a non-zero ground state energy. And one can actually relate this cosmological constant to this non-zero ground state energy. So we can calculate theoretically what is the value of this cosmological constant should be. So if we have a standard model of particle physics, what we know, and we can actually calculate the cosmological constant, what it should be, so that we can explain the observation that we get from the type 1a supernova. And when you want to match these two things, the theoretical value and of the observed value, what we get is that they are off by a factor of 10 to the power 120. So the theoretical value is 10 to the power 120 times more or bigger than what you observe through your cosmological observation or type 1a supernova. So this is a sort of an embarrassment for both cosmologists. I mean, cosmologists I would not say, because what you observe is you observe. But for the theoretician, which you actually try to explain what is this dark energy is, this is an embarrassment, because we cannot explain what is the source of this 10 to the power 120 mismatch of these two values. And that's why we very modestly call this a fine-tuning problem. Right? There's also a problem. I just what is called the cosmic coincidence problem. I just very briefly tell you what is that. That, as I said, that the dark energy and dark matter is 30% and 70%, roughly. Fine. Dark energy is the 70% of the total, and dark matter is the 30% of the total. Fine. So these are of the same order. One is around 0.7 of one is around 0.3 of one. But as you go early, you will see the dark matter the universe is completely overwhelmed by the dark matter. There is no dark energy. And as you go in the future, you will see the universe will be only dark energy. There is no dark matter. It is very, very funny that at this very present moment of our life cycle or our life, this present human life, we have the dark matter and dark energy of the same order. Fine. Had it been a bit earlier, okay, we would saw that there is no structure formed in the universe. Had it been in the very late, if something in the future, then we couldn't explain the type 1a supernova observation. So it is very funny that why our present human era is so special, that these two quantities are very, very same of order at the very present time also. This also puzzles the cosmologists. Fine. You can say that, okay, it is as it is that we have, but sometimes for the theoretician, you can say that, you need to explain that why these two completely different kind of things can be of the same order only at the present human life, but not at the very early time or very late time or in future, fine? So the theoretical problem, there's a cosmological constant problem, as I said, 120, 10 to the power 120 order magnitude defined. There is no solution yet. This cosmic coincidence problem, there is a solution that people have to get, that instead of lambda, which is a constant, people try to put something called what is called the evolving dark energy. So it is not a constant, but it evolves with time as the things evolve, like dark matter or radiation and everything, fine? Just to mention, there is a huge problem now at present, which is a huge problem for cosmologists. So if some of you in near future want to do research, you can think about it. This is one problem that nobody understands, and currently it's a completely open problem, what is called the Hubble tension. As I said, the Hubble parameter, there's a Hubble parameter in the Hubble equation, which is the H, and this Hubble parameter value at present gives you the present expansion rate of the universe, okay? So the H value at present gives you how the expansion rate or the velocity of expansion of the universe at today, fine? And this value has been observed or has been measured by two different observations. One is a very, very local observation like Hubble did with Cepheid variables and type 1a supernova, and another is by the CMB, by the Planck observation, fine? These are completely two different observations. One is more or less related to very much to the early universe, when the universe is very young, okay? And another is related to around the present time, when the universe age is around 13 billion years. Both of them measure the same quantity, the expansion rate of the universe at present, and they differed hugely. As you can see, the red points, these are the Planck measurement from the CMB. This gives you a value around 67, 68, whereas this blue point, HST and Gaia, they give you a value around 75 or 74. So there is around 10% mismatch of these two numbers. And at this moment, we exactly don't know. Nobody knows what is the source of this mismatch, because both of them are measuring the same quantity, but both of them use two different techniques. We believe both of the observations are very accurate observations, okay? But still they measure completely two different numbers. So is there something going on from the very early to recent times, or our understanding of the universe is wrong? There may be something more surprising than the dark energy. Means more dark energy is there, still we don't know what is the dark energy. But beyond dark energy, maybe there is more surprising things are there, we don't know. But this is one of the most important problems now in cosmology, okay? So there are many, many models that people have considered till now. There are models like dark energy, quintessence, and these and that. There are thousands of models. As I said, no models till now explain everything very satisfactorily, right? So what we now know for the universe, that very early time, there can be an acceleration that I have not discussed, what is called the inflation. Then the universe, there is a radiation dominated, then there is a matter dominated, and now we are going through a what is called the dark energy dominated or the lambda dominated, fine? And the universe have these 4 stages roughly, and we have more or less the 5 components. We have the photons, the lights, we have neutrinos, we have baryons, we have cold dark matter, and we have the cosmological constant, fine? So this is roughly the present picture that we have at this time. There are different ways we can actually study. We can study through this is the cosmic archaeology. We can study with the CMB. We can study with the large scale structures in the universe. We can study with the supernova and all those things, fine? And just for an observational challenge, as you can see, this has been discussed, that there means if you want to do study from your Earth, then there is only a 2 narrow window that we have. One is in the optical window, and there is a 1 narrow window in the radio window, fine? And rest of the things is actually all these wavelengths are opaque due to the atmosphere. So all those lights cannot come. So you need to do space-based observation. The ground-based observation can only be done through the optical telescope or the radio telescope. And we have these 2 future very big telescopes that we have. One is the 30-meter telescope and one is the square kilometer array. And more importantly, India is part of both these telescopes. So it's a very, and so as I said, the future projects, they are 30-meter telescope, they are square kilometer array. One is ground, both are ground-based, one is in optical, one is radio. And India is part of both of these projects. And there are also other space-based telescope and also ground-based telescope. And common goal, all those telescopes are basically to understand the dark matter and dark energy. So this is a very, very important time for cosmology, astrophysics, and astronomy. and also from the theoretical side, the general relativity and particle physics and astroparticle physics. So whoever are interested, they can actually very much welcome to work on these projects, and they can contact people in TMT or SK, the Indian people, right? So I just finished now with a quote from A Tale of Two Cities by Charles Dickens, which it says that it was the season of light, it was the season of darkness, it was the spring of hope, it was the winter of despair, and we had everything before us, and we had nothing before us. So I believe this is something that our current universe is very aptly defined. Thank you very much.
Thank you, Professor Sen. Let us join us. Let us join with me for giving thanks to Professor Anjan Sen. Professor Anjan Sen led us to cosmological tour through dark side of the universe. I hope that you have enjoyed. So if there is any question, please ask only one question, because we are all hungry. I think
yes.
And I will, if you are interested, I will give his email so that you can contact him. Yes.
Yeah, so it is can through any process of dark matter, energy may decay into ordinary matter and vice versa. Okay, so see that fact is that, okay, when I call this dark matter and dark energy and there is the ordinary matter, you have to understand that whenever you have a decay process going on, so that means the dark matter and dark energy, they should interact with the ordinary matter, fine? Now, any of these dark components, especially the dark energy interacting with the ordinary matter, is a bit troublesome, because we know that we measure gravity, or we through some local experiment, like our solar system, fine? The sun and earth motion, or the moon and earth motion, or our planetary motion, and all those things, fine? So these we know from our local observation, fine? And these are all made of ordinary matter, fine? And these are very, very precise measurements. But now, if these ordinary matter are kind of related or interacting with the dark energy, which is a dark thing, so all those things, all those means what we know can get changed. So, but as because we observe things very, very carefully, and the observations results are very accurate, so there is a very little means place to actually think that there can be interaction between the ordinary matter and some dark matter, right? Because any interaction can change the outcome of this planetary motion and all those local observations under the Keplerian motion or Newtonian gravity. And as because these observations are very, very precise and with a very, very small error bars, so there is a very little path or little way that we can do it. There can be interaction between dark matter and dark energy, and things can change it in between that. I mean, the dark matter can decay into dark energy can decay into dark matter. So those kind of things, although we exactly don't know any particle physics model that can give you such kind of interaction, but people have considered those, and they can have some observational signature, and people try to find out whether in observation we can see it. But dark matter or any dark candidate interacting with ordinary matter is a problem, because that can affect our local observation, because ultimately gravity is everywhere, right? So if you are dark matter is everywhere, dark energy is everywhere. So they can affect your local observation, and the local observations are very, very highly constant with fantastic results. So we don't think that those kind of interactions, even if they are extremely suppressed, so they don't have any effect on our local environment.
So thank you, Professor Sen, for giving
thank you very much, Professor Paul, to invite me, and I hope people have some idea, and if they're interested, they can send me emails.
Yes.
Okay.
Yes.
So primordial black holes are often considered as a possible dark matter candidate. Is there any possibility that? Okay, yeah, primordial PBH is obviously definitely is one of the leading candidate for dark matter. Fine. Till now, there is no direct detection of the dark matter, not the primordial black hole, but it is definitely is one of the very interesting candidate for the dark matter, and a lot of works are going on, and how the PBH can be formed and what kind of spectra that can have. that we can detect it for different cosmological observation that is going on. But I'm not an expert in this thing, but I don't think exactly now it is confirmed or we have a direct detection that can confirm that PBH is actually a dark matter, right? It is definitely has potential to be a dark matter, but I'm not sure that what is the current status for that.
Okay, thank you. I think once the COVID-19 pandemic situation is over, we can meet together at North Bengal University, and then there will be more discussion that time. So we hope that.
Sure.
We came
Thank
to
you
an
very
end.
much.
Thank you. Okay. I must thank Honorable Vice Chancellor of our University, Professor Subhiresh Bhattacharya, Registrar Dr. Dilip Sarkar for giving us permission to organize this webinar. It is possible to organize this seminar due to the university engineer, Mr. A. Gun, the engineers at the computer center, Mr. Anirban Vishwas, Mr. Sudeep Basu, and faculties of the physics department. I must thank my students, Mr. Sagar De and Mr. Anirban Chando, for their valuable efforts in conducting this webinar. Finally, I thank all the participants for attending this ICARD program. Hope it will be helpful for you. Then both the speakers and the organizers will be very happy. Okay, thank you. Bye. Sagar, conclude করে দাও, complete করে দাও।